This is the third series on non-stop numericals on mathematical economics. Please share, like and subscribe this channel. Let us start the series. How to find out the equilibrium basket given the different types of linear utility functions. The question is, suppose utility function of a consumer takes one of the following forms. We have three different kinds of utility function, that is u is equal to 50x plus 20y. U denotes utility, x and y are the two goods. In the second case, utility is equal to 20x plus 50y, and in the third scenario, u is equal to 80x plus 40y. Here income of the consumer is 10,000, price of good x is 50, price of good y is 20. Determine the equilibrium in each case using diagram and comment on the nature of the solutions. By equilibrium, we need to find out the equilibrium basket. Okay, I forgot to write it here. Equilibrium basket. Okay. So let's take case first. We are being given this is our utility function and we need to construct the budget constraint here. Okay, so what will consumer do in each of the case? He wants to maximize the utility derived from the consumption of two goods. We have 50x plus 20y such that price of good x times units of good x plus price of good y times units of good y should be equal to the income of the consumer. Specifically, price of good x is 50, so can we write 50x plus 20y is equal to 10,000. And let us further rewrite it, dividing both sides by 10, which gives us 5x plus 2y is equal to 1,000. Okay. Now let me draw the graph also to make the things more clear. So let us suppose I draw a simple graph. We have x good on the horizontal axis, y good on the vertical axis. Okay, so consumer wants to maximize his utility subject to the constraint that he is facing. Okay, let us draw this and we will draw the constraint and then we'll explain it. Okay, so what is the equilibrium condition or optimal condition for utility maximization? We know that at equilibrium what should happen? The marginal rate of substitution between good x and y should be equal to the ratio of the prices, that is price of good x upon price of y. This condition must hold or should hold. Okay, if this does not hold, okay, then what happens? We will see. So what is MRS? We know that MRS is simply the marginal utility of good x upon the marginal utility of good y. Okay, price of good x upon price of y, price of x upon price of y. Let's compare these two. So marginal rate of marginal utility of good x means the partial derivative of this function with respect to x, that is the change in the utility due to the consumption of good x. Okay, so derivative of this function with respect to x was 1, so we are left with 50 divided by marginal utility of good y means the derivative of the second term, which is 1 here, so we are left with 20. And what is price of good x and price of good y? That is being given us as 50 upon 20. So here we also got 50 upon 20. So what happens here? So this 0 and 0 gets cancelled, this 0 and 0 gets cancelled. Now let me explain. What does this stand for? Price of x upon price of y. It denotes the slope of budget line, and this MRS denotes the slope of indifference curve. Now what happens in this case? In the first case, the slope of the indifference curve and slope of the budget line are equal. Okay, when the slope of what we call indifference curve and slope of budget line equal, and we know that our indifference curve is linear. Okay, so what will be our equilibrium basket? Let me draw the budget line first. Let us suppose this is our budget line. Okay, this is our budget line. Now the slope of the budget line and the slope of the indifference curve is same. That means one of the indifference curve can be this IC1, but this does not maximize utility. Okay, so another can be this one, let us say IC2. This will not also maximize utility. And last one, if I draw it here, it will coincide with the budget line. So at this on this line, any point, any combination of good X and Y actually maximizes the utility of the consumer. Why? Because the slopes are equal, that is slope of indifference curve and slope of budget line are same here. Then what will be the equilibrium basket in this case? We will get infinitely many solutions here. Okay, so since this is our utility function, now one of the optimal basket can be, so since 5x, let us solve it. So we have 5x is equal to 1000 minus 2y. Okay, let us say when we have, let us say when y is equal to 5, when y is equal to 5, let me repeat, since the slopes are equal, let us suppose this is slope of the indifference curve, this is slope of the budget line, they coincide with each other. So when we solve this, so when y is equal to 5, that means 5x is equal to 10, 1000 minus 2 into 5 is 10. So it will be 1000 minus 10, which is 990, dividing both sides by 5. So we get x is equal to 5 ones are 5, 5 nines are 45, 5 eights are 40. So one of the equilibrium basket will be, that is 198 units of good X and 5 units of good Y. Okay, so let us suppose this is here 5, this is here 198. Okay, 198. This is one optimal consumption bundle. Similarly, so here we don't get the corner solution, we get interior solutions, or even we get the corner solution. If we solve y is equal to 0, so x will be equal to 1000 upon 5, so which is equal to 20. Okay, so another can be when y is equal to 10, so 5x is equal to 980, or x will be equal to 5 ones are 5, 5 nines are 45, 5 eights are 40. So another, how I am getting the same 990. So 5 ones are 5. So here it is 30. Okay, simple mathematics I am not able to do here. So we have 980 upon 5. So 5 ones are 5, actually 4. So 5 nines are 45, 5 6 3, 5 6 are 30. So 196, sorry. Another will be 196. 196. So another combination can be 196 units of good X and 10 units of good Y. Let us suppose this point. Okay, this is another optimal consumption bundle here. So here we have 198 and 5, and here we have 196 and 10. Okay, why does this happen? Because both the slopes of the utility function and the budget constraint or budget line are same here. That's why we are getting many solutions here. Okay, now let us come to the second utility function. Okay, again we want to maximize. In case of second, what we need to do, we again need to maximize u is equal to, so this time we have 20 x plus 50y subject to the constraint. Constraint is same, that is 5x plus 2y, such that 5x plus 2y is equal to 1000. Okay, again let us draw the graph. Okay, so let me draw the graph here, a very simple graph. So good X on the horizontal axis, good Y on the vertical axis. Now let's compare the slopes. So okay, so we have MRS M or S between X and Y should be equal to the ratio of the prices. Okay, so MRS is the partial derivative of this utility function with respect to X. So derivative of X is 1, so we are left with 20. Here we are left with 50. Price of X upon price of Y, it is 50 upon 20, so it is 50 upon 20. So let us remove these zeros here. So what happens here, or let me use the color combination 5 upon 2. Now here you can see 5 upon 2 is greater than 2 upon 5. And what is 5 upon 2? It is the slope of the budget line. Slope of budget line. And here you can see slope of budget line greater than slope of indifference curve. Okay, so how do I show the slope of budget line? So this is our budget line. Let me draw it like this. Okay, this is our budget line. Now the slope of the indifference curve is flatter, so it is steeper because 5 upon 2 is 2.5. It is flatter comparatively to this. So let me draw one budget one indifference curve. This will not optimize. Second can be this, third one can be this, fourth one can be this. So at a point where it intersects or it touches it, so let us say this is IC4. Okay, so IC4, at this point we are getting this touches the indifference curve. Here it intersects. Okay, you can see here. So where it touches this budget line, our utility will be maximized. So what happens at this point? At this point is we will consume X will be equal to rather 0 units of good X. Okay, because we are getting corner solution. If X is equal to 0 in this equation, then 2y is equal to 1000. So y is equal to 1000 upon 2, which is equal to 500. Okay, I hope I have done it correctly here. In the second, what happened? The slope of the budget line was steeper than the slope of the indifference curves. That is why we got the corner solution here. So what is the consumer will consume 0 units of good X and all units of good Y. When X is equal to 0 in this equation, so 2y is equal to 1000, y is equal to 500. So our optimal solution will lie here. Optimal consumption basket, or rather magenta 500. Okay, so this will be the optimal bundle here. Now in the third case, okay, let us break down the third case also. Third case we have, we again want to maximize utility, which is being given by the linear function 80x plus 40y, subject to the constraint that is 5x plus 2y is equal to 1 is 10 is 100,000. Okay, again comparing the MRS and the price ratio. So MRS will be equal to, let me write it here, MRS xy should be equal to price of X upon price of Y. Okay, color combination की तेल लेने. MRS is simply the ratio of the marginal utilities of good X and Y. So partially differentiating with respect to X gives us 5. Partially differentiating with respect to Y gives us 2. And what is the ratio of 80 upon, sorry, I have, okay, 5 upon 2 coupled square. So 80 upon 40. So we have 80 divided by 40. Okay. And what is price ratio? That is 5 upon price of X upon 5 upon 2. So here we have 4 ones are, 4 twos are. Here we have 2. Here we have 2.5. Again, slope of budget line is greater than slope of the indifference curve. Slope of IC. Okay. So if I draw the indifference curve here, so we have X and Y. Slope is 2.5, here it is 2, so it is steeper. That is, budget line is steeper, but indifference curve is flatter. And in this case, what will be our optimal bundle? That means when here x is equal to 0, x is equal to consumer will consume 0 units or no units of good x and all units of good y. That means 5x is equal to 1 is 10 is 100,000 or x is equal to 0, so x is equal to this 5x is equal to 0, so 2y. Okay, so 2y is equal to 1000 or y is equal to 500. Okay, again consumer will consume at this point where x is equal to 0 and 500 good units, 500 units of good y. Okay, if it were the case that, let us suppose we have in place of 80, let me explain the third case because we are getting the same cases here. So let me explain in the fourth one here. Agar मैं जाए वैसे, yes, I have the space, so x and y. Let me just rewrite it. Okay, so let us suppose we have the fourth utility function, that is we want to maximize u is equal to, in place of 80, let us write 120x plus 40y. So such that budget line is same, 5x plus 2y is equal to 1000. So here MRS between x and y, and we equate compare it with price of x and price of y, that is price ratio. So MRS will be here 120 upon 40, okay, using this partial derivative baggage GS. So it is 120 divided by 40, so it comes out, and price ratio is 5 upon 2. Here it is 4, oh sorry, it is 3, and here it is 2.5. In this case slope of budget line is less than the slope of the indifference curve. In this case, what will then happen eventually, if I take this fourth one to explain it? So slope of budget line is flatter than the slope of the indifference curve. So let me draw this flatter one. So let us suppose this is our budget line, and what will be the indifference curve? It will be steeper. So let us suppose one is this, second one is this, third one is this, fourth one is this. So in this case, what happens? Consumer will consume 0 units of good x, sorry, y will be equal to 0 and all units of good y. So if y is equal to 0 in this equation, so x will be equal to 1000 upon 5, which is equal to 200. Okay, 200. That means consumer will consume 200 units of good x and 0 units of good y. Okay, so I explained all the possible corner solutions. And how do you write if you want to write it? In this case, let us suppose, so in exam we can write it like this. So we write first slope of indifference curve, which is equal to marginal rate of substitution between good x and y, and when we solve it, so it will be equal to marginal utility of good x upon marginal utility of good y, and it came out to be, in any of the case, let us suppose in this case it came out to be 2. Then we compare it with the slope of the budget line. Now slope of budget line is equal to the ratio price of x upon price of y, which is 5 upon 2, which is equal to 2.5. Then we say sinus slope of indifference curve is less than slope of budget line, so consumer will consume all units of good y, consumer consume 0 units of good x and all units of good y when we solve it. Okay, so how to derive the expansion path of a firm? The question is, when the production function of a firm is q is equal to 20 times k to the power 0.5 times l to the power 0.5, price of capital is $5 per unit and price of labor is $4 per unit. Find expansion path ratio for the firm. Options are being given. We need to find out the correct option. Okay, so by expansion path, what we mean, if I draw the graph here, so if I take what we call labor on the horizontal axis, capital on the vertical axis, expansion path, we also call it scale line. It depicts the optimal combination of the inputs a firm should use to produce different levels of output while minimizing costs. Okay, so given the cost, let us suppose this is the iso cost line. So expansion path will show us the optimal combinations of inputs, while the firm minimizes its cost. That is, if I draw the ISO count here, so let us say this is one ISO count. Similarly, if our ISO cost was here, and if I draw another ISO count, likewise, if I have another ISO cost line, and if I draw another ISO count, so expansion path will join these optimal pointers. Okay, so this line will show us the expansion path of the firm. So graphically, what is meant by this? So we want to minimize cost. So what will be the minimizing? C is equal to price of labor times units of labor plus price of capital times units of capital employed, subject to the production constraint. That is, Q is equal to 20 K to the power 0.5 times L to the power 0.5. And here we can write it like this. Price of labor is being given us as 4. So we have 4 times L plus 5 times K. 5 times K. This is our cost function. Now for optimal, these pointers, what condition is required to satisfy? That is, at optimal, what happens? The ratio of the marginal rate of technical substitution between labor and capital should be equal to the price of labor upon price of capital. Okay. So MRTS, as we know, it is simply the ratio of the marginal product of labor upon marginal product of capital. It should be equal to the ratio of the prices, price of labor upon price of capital. Marginal product of capital is simply the change in the output due to the change in the units of labor employed, and marginal product of capital is the change in the output due to the change in the units of capital employed, and it should be equal to the ratio of the input prices. So it is a partial derivative of the production function with respect to labor that gives us the marginal product of labor. Likewise for marginal product of capital. Now if I partially differentiate this production function with respect to labor, and let me see if I am within the limits. I am. So when I differentiate it with respect to L, so exponent of L becomes coefficient. So 0.5 can be written as 1 upon 2, or we can write 0.5 times 20. K to the power 0.5 will remain same, but exponent of this gets subtracted by power function rule. It becomes minus 0.5. This is the marginal product of labor. Likewise, we differentiate partially with respect to K. So again 0.5 becomes coefficient. We have then 20. Exponent of K gets subtracted by 1, so it becomes minus 0.5, and L remains same as 0.5. It should be equal to the ratio of the prices that is being given us is price of labor is 4 and price of capital is 5. Okay, so 0.5, this gets cancelled, so transpose it here, it becomes K to the power plus 0.5, so it becomes K to the power 0.5 times, if I transpose it here, it becomes K to the power plus 0.5. Okay, exponent sign changes when we transpose them from numerator to denominator or vice versa. Similarly, transpose this here, so we have L to the power 0.5 first, then we multiply it with this exponent, which is minus 0.5, it becomes plus 0.5, should be equal to 4 upon 5. Okay, so bases are same, we can add up the exponent, so it becomes 0.5 plus 0.5 is 1, so here also 0.5 is 1, so we get K upon L is equal to 4 upon 5, which implies so we need to write it in the form of K will be equal to, transpose it here, it becomes 4 upon 5L, or K is equal to 4 upon 5 is, so we have 4, 5.058 are 40, so we get 0.8 L. That is the expansion path for the given firm. The solution to minimization problem, that is minimize y is equal to x1 plus x2 subject to the constraint 1 minus under root x1 minus x2 is equal to 0 is options are being given. We need to find out the correct option here. Okay, so what is our question? We have to minimize y is equal to x1 plus x2 subject to the constraint that is 1 minus under root x1 can be written as x1 is power 1 upon 2 minus x2 is equal to 0. Okay, so we will form the Lagrange's function first. To form the Lagrange's function, what we do, we multiply the constant both sides by lambda. Okay, so we have lambda times this is equal to lambda times 0, which is 0. Then we form Lagrange's, which is equal to the objective function, which is x1 plus x2. Then we add this resulting constant, that is plus lambda 1 minus x1 raised power 1 upon 2 minus x2. Okay, to find out the optimal values of x1 and x2, what we do, we partially differentiate this Lagrange's function with respect to x1 and x2, solve them simultaneously then, and set them equal to 0. So that means L subscript 1 means the partial derivative of this function with respect to x1. Derivative of x1 is 1. Then here the derivative of x1 raised power 1 upon 2 is, it becomes 1 upon 2 x raised power minus 1 upon 2 by power function rule. If we have x1 1 upon 2, its derivative is 1 upon 2 becomes coefficient x1 and exponent is subtracted by 1. So 1 upon 2 minus 1 is minus 1 upon 2, and here we have negative sign, here will be also negative sign. So we have derivative of a constant is 0, derivative of this comes out to be minus times, first we have lambda 1 upon 2 x1 raised power minus 1 upon 2. Then L2 means the partial derivative of this function with respect to what we call x2 this time. Okay, so derivative of x2 is 1, derivative of x2 is here 1, so we are left with minus lambda only, and we set it equal to 0. This also set it equal to 0, and let us rewrite it. So we can write 1 is equal to lambda 1 upon 2 x1 raised power minus 1 upon 2, and here in this equation 1 is equal to lambda. Okay, then we need to differentiate with respect to lambda. Okay, so derivative of lambda is 1, we are left with 1 minus x1 raised power 1 upon 2 minus x2, and we set it equal to 0. Let us say this is equation first, this is equation second, this is equation third. Now dividing equation 1 by equation 2, so equation 1 by equation 2, we get 1 upon 1 is equal to lambda times 1 upon 2 x raised power minus 1 upon 2 divided by lambda. Okay, so lambda gets cancelled, we are left with 1 upon, transpose it to the denominator, so its exponent becomes positive, is equal to 1, which implies twice x1 raised power 1 upon 2 is equal to 1, which means x1 raised power 1 upon 2 is equal to 1 upon 2, or x1 is equal to, transpose it, it becomes square 1 upon 2 square, which is equal to 1 upon 4. So the value of x1 is equal to 1 upon 4. To find out the value of x2, we plug x1 is equal to 1 upon 4 in equation third. Okay, so which implies 1 minus x1 is this 1 upon 4 raised power 1 upon 2 minus x2 is equal to 0, which is equal to 1 minus, so this can be written as 1 divided by 2 square raised power 1 upon 2 minus equated to x2, which implies 1 minus, so 2 gets cancelled, we are left with 1 upon 2 is equal to x2, subtract 1 upon 2 from 1, so we'll get x2 is equal to 1 upon 2. So x1 came out to be 1 upon 4, x2 is equal to 1 upon 2. That means the correct option. How to find out the equilibrium level of income from the investment and savings function? The question is given the investment is equal to 50 plus 0.25y, where I denotes the investment, y denotes the income. Savings is equal to minus 150 plus 0.4y. G is the government expenditure, which is being given us here 50, which is autonomous. Here we need to find out the equilibrium level of income. Okay, so first thing is first, there we know that our total income is either consumed or it is saved. That means consumption plus savings will give us the total income. Now we are being told that savings function is being given. Can we write y is equal to c? So savings is minus 150 plus 0.4y. So we need to solve for consumption function, because we know our national income identity is, that is total income will be equal to consumption expenditure plus investment expenditure plus government expenditure. Okay, so we need to find out the value of C first. So can we write C is equal to, transpose this here, it becomes plus 150, then we have Y, transpose it, it becomes minus 0.4Y, or our consumption function will be 150. When we subtract 0.4Y from Y, we will get 0.6Y. Okay, this is our consumption function. Now we know that our total income will be equal to consumption expenditure, that is 150 plus 0.6Y plus investment expenditure, that is being given as 50 plus 0.2Y plus 50 plus 0.2Y, and the government expenditure, which is 50. So we have 150 plus 50 plus 50, so it becomes 250. Here 0.6Y plus 0.2Y is 0.8Y. Okay, subtract it from Y, so we'll get Y minus 0.8Y is equal to 250, which implies 0.2Y is equal to 250, and 0.2Y can be written as 2 upon 10Y is equal to 250, which implies Y will be equal to 250. Transpose it here, it gets multiplied but reciprocated 10 upon 2, so Y will be equal to 250 to 2500 upon 2, so Y will be equal to 1250 here. Okay, that means our equilibrium level of income will be 250, so B option should be correct. How to find out the minimum and maximum point of a given function? The question is given Y is equal to x cube minus 12x squared plus 36x plus 8. Find the point is where the function reaches minimum and maximum. Okay, so we are being given y is equal to x cube minus 12x squared plus 36x plus 8. This is our given function. Okay, so if I draw a simple graph, okay, so if I can draw it, so we have x on the horizontal axis, y on the vertical axis. So drawing a rough graph, so let me try to draw the graph. Okay, this is our y function. Okay, we need to find out the points where this function reaches maximum and minimum. Okay, so first order condition, that is first order condition for optimum requires that we take the slope of this function and set it equal to 0 to find out the point where slope is equal to 0. Okay, so that means dy upon dx. Okay, so first order condition is simply we find out the point where slope is equal to 0, so that means dy upon dx should be equal to 0. Okay, this condition satisfies the condition where slope of the function is equal to 0, which dy upon dx is derivative of this function with respect to x, so we get 3x square minus 2 into 12 is 24x plus 36, and derivative of constant is 0, and we set it equal to 0. Okay, so solving this will give us the point where the slope of the function is equal to 0. Now you know, since 3 is divisible by 3, 24 is divisible by 3, 36 is divisible by 3, so let us divide both sides by 3, so we will get x square minus 8x plus 12 is equal to 0. So this is our quadratic function, and we can solve it using splitting middle term. That means x square, so in place of minus 8x can we write minus 6x minus 2x, and in place of 12 can we write minus 6 times minus 2, so splitting middle term using quadratic formula. So let us take x common from the first two terms, so we are left with x minus 6, and let's take minus 2 common from the last two terms, we are left with x minus 6, and we set it equal to 0, this also equal to 0. Now how do I got this minus 8x equal to minus 6x plus minus 2? It is very simple. Given this quadratic function in standard form, we should get sum of the two numbers should be equal to the coefficient of the middle term, which is minus 8, and the product of the same two numbers should be equal to the constant term, which is equal to 12. Okay, here you can see when we write here minus 6 and minus 2, it satisfies minus 6 and minus 2 is minus 8, and minus 6 times minus 2 is equal to minus into minus is plus, so we get 6 2s are 12. That's how we got minus 6x minus 2, that is this minus 6 and minus 2 is equal to minus 8x, plus in place of this we write minus 6 times minus 2, which is plus 11, sorry, plus 12. Okay, having said that, let's take x minus 6 common. We are left with x minus 2 and we set it equal to 0, which implies here either x minus 6 is equal to 0 or x minus 2 is equal to 0. X minus 6 is equal to 0 means x is equal to 6. X minus 2 is equal to 0 means x is equal to 2. So we got two critical points where the function has slope equaling 0. Okay. So this is first order condition, that the slope of the function should be equal to 0. Now second order condition is that the point where slope is equal to 0, at that point the slope should be, that is d square y upon dx square, which should be less than 0, or slope should be decreasing, less than 0, negative slope. Okay, for it is a condition for maximum, and for d square y upon dx square, when we evaluate it at the critical points, it should be greater than 0 for minimum. Okay, now let us take it one by one. So first we need to find our second order derivative, d square y upon dx square. Okay, and we evaluate it at critical points. So this is the first derivative, dy upon dx. Now the derivative of first derivative gives us second derivative. So again differentiating this with respect to x. Derivative of x square is 2x, so 2 into 3 is 6x, 6x, minus derivative of x in the second term is 1, so we are left with 24. Now we evaluate it at critical point. So d square y upon dx square, when we evaluate it at x is equal to 6, first x is equal to 6, so plug the value. So we have 6, in place of x we write 6 again, minus 24, so it is 36 minus 24, which is equal to 12, which is greater than 0. So this point x is equal to 6 satisfies the condition for minimum. Okay, because we got d square y upon dx square greater than 0, and it satisfies the condition for minimum, relative minimum. So at this point we will have minimum value of the function. Now let us evaluate that x is equal to 2. So d square y upon dx square, then we evaluate it at x is equal to 2, will be equal to, so 6 times the value of x is 2, minus 24, so it is 12 minus 24, which is minus 12, so which is less than 0. So this point satisfies the condition for, since it is less than 0, this very condition, it satisfies the condition for maximum. So at this point the function will have maximum when x is equal to 2. Okay, so first order condition gives us the slope is equal to 0, so this is FOC, that is slope is equal to 0. Second order condition tells us the second derivative should be less than 0, that is d square y upon dx square should be less than 0 for minimum, for maximum. And at this point when we evaluate it, d square y upon dx square, it should be greater than 0 for minimum. Okay, so when slope is equal to 0, that means dy upon dx is equal to 0 at this point, and at this point also slope is equal to 0, dy upon dx is equal to 0. So this condition, so this function reaches its relative minimum at x is equal to 6 and relative maximum at x is equal to 2. I have a question on definite integrals. The question is, the number p solves the following equation, that is the definite integral from 0 to p of function e raised power 2x with respect to x is equal to 1. What is the value of p? Okay, so for that what will we do? We have the definite integral, that is from let's write it here. So we have 0 to p e raised power 2x dx is equal to 1. So integrated with respect to dx, which implies, so can we write it like this, e raised power 2x, its derivative is equal to e raised power 2x divided by 2, and we evaluate it from 0 to p and set it equal to 1. Why? Because the derivative, or sorry, the integral of e raised power nx comes out to be e raised power nx divided by the coefficient of the exponent of x, which is n. Okay, that we have used here. So now let's evaluate this definite integral at upper limit, which is p, and then subtract and evaluate it at lower limit, which is 0. So evaluating at upper limit means e raised power 2 times x, the value of x is p, so we have 2p divided by 2. Then we subtract and evaluate it at lower limit, so we have e raised power 2 times 0 and divide by 2, and it should be equal to 1. So we get here e raised power 2p upon 2 minus e raised power 2 times 0 is 0, e raised power 0 is equal to 1. So we get 1 upon 2 should be equal to 1, which implies bases are same, denominator is same, we can subtract the numerator. E raised power 2p minus 1 divided by 2 is equal to 1, and we can write it like this: e raised power 2p minus 1 is equal to, transpose it here, it gets multiplied, or e raised power 2p is equal to 2 transpose it becomes plus 1. So e raised power 2p is equal to 3, but we need to find out the correct option here. So let us take the log on both sides. That means natural log of e raised power 2p is equal to natural log of 3. Okay, now natural log of e raised power 2p is equal to 2p becomes coefficient to 2p times natural log of e should be equal to natural log of 3. Okay, I have the space here, so we get here 2 times p, the log of e is equal to 1, so we get 2p is equal to ln of 3, which implies p will be equal to ln of 3 upon, transpose it here, it gets divided, which is equal to 1 upon 2 ln 3. That means option B should be correct. The question is solve for x, that is x square minus x cube is equal to 2. We need to find out the value or values of x. Okay, so can we write it like this? We have x square minus x cube, transpose it here, it gets negative 2, and we set it equal to 0. This is first thing. Then what will we do? Let us write x square minus x cube, and minus 2 can be written as negative 1, negative 1. So negative 1 and negative 1 is negative 2, and we set it equal to 0. Now what will we do? Let's write it again. So we have x square minus x cube minus, let's take minus common, we have 1 plus 1 is equal to 0. Then we write x square minus x cube minus, now in place of 1 let me write it 1 square, and in place of this one I write 1 cube. Okay, so 1 square is equal to 1, and 1 cube is also equal to 1 into 1 into 1, which is again equal to 1. Okay, and we set it equal to 0. Then we have x square minus x cube, then minus 1 square minus 1 cube is equal to 0. Now let's write these two terms first. So we have x square minus 1 square, then we have minus x cube, then minus 1 cube, and set it equal to 0. Now we have here x square minus 1 square. Okay, and let us take minus 1 common here. So let's take minus common, we are left with x cube plus 1 cube, and we set it equal to 0. Now this term x square minus 1 square, this resembles to a square minus b square, and we know it is equal to a plus b times a minus b. Likewise here we have x plus 1 times x minus 1. Okay, these are the identities. We know that a square minus b square is equal to this stuff. So in place of a we have x, in place of b we have 1, so we can write it like this. So here we write x plus 1 times x minus 1. Okay, then we have minus. Now what is a cube? We have rather x cube plus 1 cube, and we know that a cube plus b cube is equal to, this is equal to a plus b times a square plus b square minus 2 times a b. Okay, likewise in place of a we have x, in place of b we have 1. So can we write it like this? X plus 1 times a square means x square, b square means 1 square, minus 2, in place of a we have x, and in place of b we have 1. Okay, So we can write it like this. So in place of this we write x plus 1 times x square plus 1 square minus 2 times x. 2 into x into 1 is x, rather 2x. Now let me rub this out. Solving further, so we have x plus 1 times x minus 1. Okay, so what will be, and we set it equal to 0 obviously. Now rewriting this, so can I write it like this? We have x plus 1 times x square minus 2x plus 1, and we set it equal to 0. Solving further, so solving means we have x plus 1 times x minus 1 times we have x plus 1 here. So let me see if I am doing it correctly. So we have x plus 1 x square minus 2x plus 1, or we can do one thing here to save the space. Let us take x plus 1 and x plus 1 common. So x plus 1, when we take it common, we are left with this x minus 1. Okay, then we have, so here we have minus. Okay, so when we take x plus 1 common, we are left with x minus 1. Then we have minus times x square minus 2x plus 1 is equal to 0. Okay, so I have taken this very term common, x minus 1 and x minus 1, sorry, x plus 1 and x plus 1. Then we are left with x minus 1 here, then we have minus, then we have this term. Again solving this, so we have x plus 1 times, okay, here we have x minus 1, so we have x minus 1, then we have minus x square, minus into minus is plus 2x, then we have minus into plus is minus 1. Okay, or we have x plus 1. Okay, let me see if I am doing it correctly. So we have x, somewhere I am doing it incorrectly. A square. Okay, so here I have done a mistake, because we know that a cube plus b cube is equal to a plus b times a square plus b square minus 2 into a into b, rather minus ab. 2 is not here, so this 2 is not here, and it is not here, it's not here, and obviously it is not here. Okay, so this is the correct formula, that is x cube plus 1 cube will be equal to x plus 1 times x square plus b is 1 square, then we have minus x times 1, so there is no 2 times here. So what happens here, we have x plus x, which is 2x, negative 1 and negative 1 is negative 2, then we have minus x square, and it is equal to 0. This is also equal to 0. So can we write it like this, x plus 1, then we have, let's write it in the standard form. First we write minus x square, then we have plus 2x, then we have minus 2. Okay, I am just rewriting them so that we know that subtraction, or rather addition, is also commutative for integers, and we set it equal to 0. Now what does this expression tell us? This tells us, rather this equation tells us either x plus 1 is equal to 0, or this minus x square plus 2x minus 2 is equal to 0. If this is the case, that means x will be equal to, transpose it here, it becomes negative 1. Now if this happens, that means we need to solve it to find out the value of x again. So let's write it let's multiply both sides by -1. So multiplying by -1 here, so -1 here and here, so we will get x square minus 2x plus 2 is equal to 0. Now solving using the quadratic formula. So we know that if we have ax square plus bx plus c, the value of x is equal to minus b plus minus b square minus 4 times a times c divided by 2 times a. Now in place of a, we have here x square minus 2x plus 2. Okay, so it is equal to 0, this is equal to 0. Now here in place of x, so x will be equal to, so the coefficient minus b means the coefficient of x, which is, first we have negative from the formula, then we have minus 2 plus minus b square means negative 2 square, then we have negative 4 times a, the coefficient of a is 1, then we have constant term which is 2. Okay, divide 2 times a is obviously 1 here, that gives us x is equal to minus into minus is plus, so we get 2 plus minus, now negative 2 square means positive 4, you know square of a negative number is positive, then we have minus 4 2s are 8 divided by 2, or x is equal to twice plus minus negative 4 divided by 2, which can be written as x is equal to, or let's write it here, so we get a 2 plus minus, so negative 4 can be written as negative 4 times, rather 4 into negative 1, 4 into negative 1 divided by 2, or x is equal to 2 plus minus, so let us simplify it, can we write it here 4 times negative 1 divided by 2, which is equal to 2 plus minus, now square root of 4 is 2, then we have negative 1 upon 2, or x is equal to, let us take 2 common, so we will get, let us take 2 common, we are left with 1 plus minus under root 1 divided by 2, so 2 gets cancelled, that gives us x is equal to 1 plus minus negative 1. Okay, that means now we know that under root of negative 1 is equal to iota. Okay, so can we write x is equal to 1 plus minus iota, or x is equal to 1 plus iota, or x is equal to 1 minus iota. That means, so that means x1 is equal to 1 plus iota, x, rather since x, let us say the value of x is here x1, that means we got 3 values for x, that is x1 is equal to negative 1, second is x2 is equal to 1 plus iota, and x3 is equal to 1 minus iota. So we got 3 values for x, that is x1, x2, x3 is equal to negative 1, 1 plus iota, and 1 minus iota. We will solve a question on Leontief utility function. The question is, suppose utility of a consumer is given as utility is equal to minimum of x1 comma x2 upon 3, where x1 and x2 are the two goods and u denotes the utility derived from the consumption of these goods. The consumer buys 30 units of good x2. What is the consumer's income if price of good x2 is $4 and price of good x1 is $2? Okay, so we have the utility function, that is utility derived by consuming x1 and x2 is being given by minimum of x1 comma x2 upon 3. Okay, so let us first understand what is this utility function. So utility derived is equal to minimum of whatever is in the brackets x1 comma x2 upon 3. x1 and x2 denotes the units of good x1 and x2. Now this utility function, we call it the Leontief utility function, or we call it perfect complementary utility function, or we call it the fixed proportion utility function. So let me explain with a simple example. Let us say we have a normal consumer. He goes to a shop. By normal consumer I am saying who is not specially able, who has two legs. Okay, perfectly a healthy person. He goes to a shop, so he wants to buy a pair of shoes. Okay, so he will choose left shoe and right shoe. Okay, so and let us suppose he chooses L and R. These are the pair of right and left shoe. Sorry, a pair of shoe with left and right shoe in it. So let us suppose he gets a utility of 10 from this very thing by purchasing. Now if this person tells the shop, give me 2 left shoe and 1 right shoe, okay, what utility he will get? He will get only 10 again, because this extra left shoe will not serve him anything. Okay, by the same likewise we can say if he chooses only 1 left shoe and 2 right shoe, again his utility will be same. Let us suppose we get this arbitrary number here, 10 units. Now if he chooses 2 left shoe and 2 right shoe, here his utility will increase. Let us suppose it goes to 20. So what we are visualizing here, consumer will choose a certain goods in a fixed proportion, okay, in some fixed proportion. That means 1 left shoe and 1 right shoe, if it gives him a utility of 10. If we double left shoe and right shoe, let us say 2L and 2R, then only his utility will increase. Let us suppose 20. Only increasing 1 unit without increasing the other unit will not increase the utility of the consumer. That is the essence of the Leontief utility function, where the consumer consumes goods in a fixed proportion. Changing the proportion will not help in increasing its utility or her utility. English gaya tel lene. Having said that, so this is our main function, Leontief utility function. We are also being told the price of good X is X1 is $2, price of good X2 is $4, and income of the consumer is, we need to find out. And we are also being told consumer consumes 30 units of good X2. So let us say X2 star is 30. Given this information, we need to find out the expenditure or income of the consumer. Now what will we do? We put X2 is equal to 30 into the main function. Okay, so when we plug it, so utility of the consumer will be equal to minimum of X1 comma X2 is 30 divided by 3, which is equal to minimum of X1 comma 30 upon 3 is 10. Okay, so U is equal to min of X1 comma 10. So how do we find out the equilibrium level of X1 for this consumer? So what we do when we have the min function, we equate whatever is in the parenthesis. That means X1 will be equal to 10. That means consumer will consume 10 units of good X1. Then his utility will be maximum. Okay, and let me explain it here. As long as X1 is greater or equal to 10, consumer's utility will be maximizing. Okay, so if X1 is equal to 10, so what will be the consumer's utility? So utility will be equal to minimum of X1 is 10, you go a bracket 10 divided by X2 upon 3, X2 upon 3, 30 upon 3, which is 10. Here you can see, so utility will be equal to 10. Let us suppose X1 is greater than 10. Let us suppose 11. So in this case, utility will be equal to minimum of, so here we have 11, and x2 comes out to be 30 upon 3, which is 10. Here we also get the same utility. If we decrease x1 to 8, let us suppose utility will be equal to minimum of, in place of x1 we have 8, and this is here 10. Here you can see, and the lesser of the two is 8, so consumer's utility will decrease. So he will increase his utility only if he consumes x1 equal to 10 or greater than 10. But at optimum he will choose 10 units of good x1. Okay. Having said that, now what will be the total expenditure of the consumer? We know that consumer will maximize his utility U is equal to min of x1 comma x2 upon 3. We know that, subject to the constant. What is the constant he is facing? That is price of good 1 times units of good 1 plus price of good 2 times units of good 2 should be equal to the income of the consumer. Price of good 1 is being given us as 2, so we have 2 times, at equilibrium he consumes 10 units of good x1 plus price of good 2 is 4, and at equilibrium we know he consumes 30 upon 3, which is 10 here. Okay, which will be equal to m. So 2 tens are 20 plus 4 tens are 40 is equal to m. That means the share. So consumer's total income will be equal to $60 if he consumes the goods in the given proportion. So to find out the level of income where savings is equal to 0 from the consumption function, the question is, if C is equal to 100 plus 0.75 y, where C is the consumption spending and y is the income, solve for the level of income where savings is equal to 0. Okay, so we have the consumption function as C is equal to 100 plus 0.75 y. C is the consumption. 100 denotes the autonomous consumption when the level of income is 0. 0.75 is the marginal propensity to consume, and y denotes the income. Okay, so this is our consumption function. Now we know that our total total income is equal to the consumption expenditure plus, or we can say total income is equal to consumption plus savings. Okay, so if our total income is 100 and if we consume 80 units, then 20 units will be the savings. Now here we are being told that savings is equal to 0. So S is equal to 0. That means Y is equal to C. Okay, so our total income is equal to the consumption expenditure. Now that means Y is equal to, what is consumption expenditure? That is 100 plus 0.75 Y. Now transpose this to LHS, it gets subtracted, is equal to 100, or it becomes 0.25 y is equal to 100, which implies 0.25 y can be written as 1 upon 4, y is equal to 100, okay, or y is equal to 100, transpose it here, it gets multiplied. That means total income or our level of income will be equal to 400 here. Okay, so simple thing, our income is either consumed or saved. Since savings is equal to 0, our income is equal to consumption expenditure, then we solve for income to get the level of income where savings is equal to 0. We will learn about the different types of utility functions and how the consumer attains the equilibrium. So we will take the Cobb-Douglas utility function in this case. Okay, so let's take the Cobb-Douglas utility function. That is, we have the first case of Cobb-Douglas utility function. So in this case, what happens? It is general form. First we write the general form. So general form of Cobb-Douglas utility function is, that is, utility is a function of two goods, let us say x and y, and it is equal to x to the power a times y to the power b. This is the standard Cobb-Douglas utility function, where x and y are the two goods and a and b are the two constants. Here a, b are the constants, Okay, so let us suppose their consumer is facing this kind of utility function, what we call the Cobb-Douglas utility function. Now in this case, let us also assume that we have the budget constant, that is price of x and units of good x plus price of y times units of good y, and it should be equal to the income of the consumer. Okay, so given this standard Cobb-Douglas utility function, if the consumer wants to maximize his utility, so we will take utility here, utility maximization problem. So consumer will try to maximize his utility derived from the goods x and y, which is equal to x to the power a times y to the power b, and he will face some constant that is such that price of x times units of good x plus price of y times units of good y should be equal to the income of the consumer. So our problem is, in case of Cobb-Douglas utility function, we need to maximize the utility subject to the budget constraint. Okay, having said that, what we are going to do here, we want to find out the optimal bundle that the consumer will choose. Okay, so for optimality, the condition is that we equate the marginal rate of substitution between good x and y with the ratio of the prices, price of x and price of y. This denotes the slope of indifference curve, and this denotes the slope of budget line. Okay, slope of budget line. MRS, as we know from earlier videos, it is simply the ratio of the marginal utilities of good x and marginal utility of good y, and we equate with price of x and price of y. Okay, so to calculate marginal rate of substitution between good x and y, we take the ratio of the marginal utilities, and we know that marginal utility of good x is the change in the utility due to the change in the units of good x consumed divided by MUY. Likewise is the change in the utility due to the change in the consumption of good y. It should be equal to the ratio of the prices, that is price of x divided by price of y. Okay, so let us take a simple graph here also to make things clear. So we have good x on the horizontal axis, good y on the vertical axis. So let us suppose consumer is facing this budget line, budget constraint. So this is our budget constraint. With the given budget, consumer wants to achieve highest satisfaction, and this condition actually is a point of optimality, the point where the indifference curve and the budget line is tangent. That will give us the optimal units of good x and y. That will give us the x star and y star. So x star denotes the demand function also of good x, and y star denotes the demand function of good y. So we need to calculate that very thing. So we have, so this is a point of tangency here. So it is also called the tangency condition, where the marginal rate of substitution between good x and y is equal to the ratio of the prices, price of x and price of y. So px py denotes the slope of this budget line, MRS is the slope of the indifference curve. So du upon dx, that is the partial derivative of utility function with respect to x. We need to find out, we have this utility function, let's take its partial derivative with respect to x. By using power function rule, exponent of x becomes coefficient, so we have a times x, and exponent is subtracted by 1. Y raised power b remains the same because we are taking partials. Okay, so that's the partial derivative of utility function with respect to x. Likewise, we take partial derivative with respect to y, so it will become b, x raised power a remains same, but the exponent of b will be subtracted by 1, and we equate it with the ratio of the prices, price of x upon price of y. We will also solve a specific problem here. Okay, so let me try to take the general form here. Okay, so doing some simple algebra, we can write it like this. So let me write it here. So we have a upon b. Okay, so transpose this y to numerator, so we have y raised power b first here, and when we transpose it here, so it will become y raised power minus b plus 1, because when we transpose denominator to numerator or vice versa, exponent sign changes. Likewise, we have x to the power a here. If I transpose this x to the power a minus 1, it will get multiplied, but it is exponent will change. So if where we have a, it becomes minus a, minus 1 becomes plus 1. Okay, so I am just solving this stuff here. Here bases are same, we can add up the exponents. So we have a upon b, y raised power, so we have b minus b plus 1, and in the denominator we have same basis, we can add the exponents. We have a minus a plus 1, and here you can see it is a upon b. B and b gets cancelled, we are left with y raised power 1, and here we are left with x raised power 1, which is equal to a upon b times y upon x. Okay, so when we solved this thing, we got a upon b times y upon x is equal to px upon py. Okay, now I can rub this out. Okay, let us solve it for y first. So if I solve it for y, and let me solve it here, so we have a upon b. Okay, or let us solve it step by step. So we have y upon x first is equal to, transpose it here, it becomes b upon a, px upon py. Okay, now transpose this x, so we will get y is equal to b upon a, px upon py times x. Okay, so we got here y is equal to b upon a, px upon py times x. Rather, okay, so we solved it. I don't have space, that is why I am doing the calculation here. Now we plug this value of y into the budget constraint. So let us plug the y here. So we will get price of x times units of x plus price of y. In place of y, we have now b upon a, px upon py times x. So py gets cancelled, and we can take x first common. Okay, x and px. If I take x times px common, we will be left with 1 plus b upon a. Okay, and it should be equal the income. Usme mashti go magaz us khabar kape. Solving further, so x times p of x, so it becomes a plus b upon a is equal to m, or we can write x is equal to, so we have m here, transpose this here, it gets divided, so we have a plus b upon a. If I transpose it, it becomes a divided by a plus b. So here, okay, that means x is equal to m times a divided by a plus b px. This is the demand function for good x. Okay, we also call this Marshallian demand function. When the demand is a function of income and prices, we say it is a Marshallian demand function. Okay, so this is our demand function for good x. Likewise, if I plug this value in this equation, we will get the optimal bundle for y will be equal to m times b divided by a plus b times py. Okay, this is how we solve rather the optimization problem, rather constrained optimization problem, when the individual is facing a Cobb-Douglas utility function. Okay, so let's take the specifics here. Okay, let me take a simple example here. Let us suppose we have a consumer, so we want to maximize utility of the consumer, and let us suppose utility function is x times y. So it is in the standard form here, a and b is 1 and 1 here, such that let us suppose price of good x is let me write it here, px into x plus py into y should be equal to m. Let us take price of good x is 1, so we have x plus price of good y, let us take 2 times y should be equal to, so price of good y is 2 and it should be equal to income. Let's take any arbitrary income here, let us say 12. Okay, so using this equation, how do we solve it? So first order condition for optimization requires that rather we take the tangency condition, we equate MRS with ratio of the prices. MRS, as you know, it is the partial derivative of utility function with respect to x. Partial derivative with respect to x gives us as y. Partial derivative with respect to y gives us as x, and it should be equal to the ratio of the price. Price of x we take 1. We have assumed here it is equal to 1 upon price of good y is 2. Solving for y, y will be equal to, transpose it here, it becomes x upon 2. Now we plug this value of y into the budget constraint here, so we will get x plus 2, so value of y is x upon 2, 2 gets cancelled and it is equal to 12, so 2x is equal to 12, that gives us x will be equal to 6. So consumer will consume 6 units of good x, and how many units of good y? So y will be equal to x upon 2 means 6 upon 2, which is equal to 3. So y is equal to 3. Graphically, what is meant by this? So we have x on the horizontal axis, y vertical axis. We have this budget constraint and we got the optimality at this point. At this point, consumer will consume 6 units of good x and 3 units of good y. Okay, in this specific case. So this was about Cobb when the consumer is facing Cobb-Douglas utility function. In the next video, we will learn about the what we call, so let us take a linear utility function when the consumer is facing the linear utility function. Okay, now let us take another utility function, and how does the consumer optimizes or maximizes his utility we will discuss. So we have this time the linear utility function. So it is general form is that is utility derived from the consumption of two goods x and y is equal to a times x plus b times y. Okay, so this is our general utility function. So this is linear in two goods x and y here, that is utility derived from good x and y is equal to a times x plus b times y. A and b are the two constants here. So let's take the budget constraint also. Let us say price of good x times units of good x plus price of good y times units of good y should be equal to the income of the consumer. Okay, so consumer's endeavor, as we know, is to maximize this stuff. So maximize utility subject to this budget constraint. Okay, now how do we solve this kind of utility function? We have three cases in this case, in this type of utility function rather. So let us first draw a simple graph to explain all the cases. So let me take the first one. So we have good x on the horizontal axis, good y on the vertical axis. So we take the first case. Okay, so first thing is what we do, we equate marginal rate of substitution with the price ratio. Okay, so for optimization, or for equilibrium in this case, what happens, we equate the marginal rate of substitution with the ratio of the prices. Okay, as we know, MRS is simply the marginal utility of good x upon marginal utility of good y, okay, which is equal to the change in the utility due to the change in the consumption of good x. MUY means the change in the utility due to the change in the consumption of good y. We know this very thing. So in this case, what is the MRS? MRS will be the derivative of this function with respect to x first. So we get the derivative of x is 1, so we are left with a divided by, let's take the partial derivative with respect to y, we get b, and here we have the ratio px and py. Okay, now what do we do? we observe the slopes. As we know, MRS is the slope of the indifference curve. Px and Py, Px upon Py is the slope of the budget line. And let us draw the budget line here. We have three cases here. So since this denotes the slope of IC, this denotes the slope of budget line. First case will be here. So first case is if this A upon B, if the slope of indifference curve is greater than the slope of budget line. And let us draw here the budget line. Let me draw. Let us suppose we have this kind of budget line. This is our budget line. Slope of indifference curve is greater if the slope of indifference curve, that is if A upon B is greater than Px upon Py. So we will draw a steeper indifference curve in this case, since we have the linear one. So first one could be like this. So let us suppose this is first indifference curve, then we have second indifference curve, and let us suppose this is our third indifference curve. So this is our IC3. Okay, when this is the case, when the slope of the indifference curve is greater than the slope of the budget line, so we will get a corner solution. That means we get here corner solution, and consumer will consume 0 units of good Y, because the indifference curve and budget line, obviously this will not increase, maximize the utility. This will not also maximize the utility. So consumers endeavor is to reach to the highest possible indifference curve. Okay, so highest possible indifference curve is possible at this corner, where the indifference curve 3 touches the budget line. So what happens in this case? Consumer will consume, since we are at this point, Y is equal to 0 here. So that means if this is the case, consumer will consume 0 units of good Y and all units of good X. Okay, so how many units of good X? Plug Y is equal to 0 in the budget constant. So this term is equal to 0. That means price of X into X is equal to M. That gives us X will be equal to total income divided by price of good X. So consumer will consume all units of good X. So this point denotes a point where we have the utility bundle, rather optimal bundle, that is this very thing. Okay, so this was the first case when the slope of indifference curve was steeper than the slope of the budget line. Let us take the second case, and let me draw the graph also. So we have good X and good Y. Second case will be when A upon B, that is the slope of the indifference curve, is less than the ratio of the prices. Okay, that means in this case this is steeper. Okay, so budget line is steeper comparatively. So let me try to draw magentas. Let me try to draw a steeper budget line in this case. So let us suppose this is our steeper budget line. So this is budget line, and MRS, which is slope of the linear indifference curve, it is flatter this time. So let us draw the flatter one. So one can be this, another can be this very indifference curve, and third one will be this. So let us say this is IC3. So when the budget line is steeper than the indifference curve, in the second case what happens? Consumer will consume 0 units of good X, 0 units of good X, and all units of good Y. And how many units of good Y? Like X is equal to 0 here, we get Py times Y is equal to M. So consumer will consume all units of good Y, and that will be equal to total income upon the price of good Y. So we will get at this point the corner solution or optimal bundle, that is 0 units of good Y and all units of good, or rather 0 units of good X and all units of good Y. Okay, this was case second. Now we have third case. Third case can be when the slope of the indifference karo shamat gona, when the slope of the indifference karo, okay, so is equal to the ratio of the prices. So let me draw the third case also. So we have x and y. So in this case what happens, let us suppose this is our budget line, okay. Since slope is same, one indifference curve can be this IC1, it will not maximize utility. Another can be IC2, and another indifference curve which coincides with the budget line, so that will maximize the utility of the consumer. So in this case what happens, in this case what happens, we get infinitely many solutions. So we get many optimal bundles, because the indifference curve and the budget line coincide with each other. So we can get, if I write, we can get here the optimal bundle, here, here, here. That means any combination of good x and y will maximize the utility. And let us see what is meant by this. So what we do, we take the budget constant and solve for, let us say, x. So we have px into x is equal to m minus py times y. So when y is equal to 0 in this case, so x will be equal to m upon okay, when x is when y is equal to 0, so we get x is equal to m upon px. So one we get the corner solution also here, that is we get m upon px, and this can be one bundle, okay. So when y is equal to 1, so when y is equal to 1 in this equation, so y is equal to 1, so we get x will be equal to m minus py divided by px, okay. So we will get this bundle. When y is equal to 1, so we get m minus py divided by px and 1. This will be another, you know, the optimal bundle. Similarly, when y is equal to 2, 3, 4, and we will get infinitely many solutions when the slope of the linear utility function or indifference curve is equal to the slope of the budget line, okay. So let us take the specific example to make things clear to you, okay. So let us take the specific example here. This was the general form. Now we take the specific example. Let us suppose we have a utility function. We want to maximize u is equal to, let us take a simple case, x plus y, subject to, let us take the price of good x this time. Let us say price of good x is equal to 1, price of good y is equal to 2, and income of the consumer is 6, okay. So again we equate m or s with the ratio of the prices, that is px upon py, and we also need to, okay, so let me first draw the budget line. So what will be the budget constant, that is px into x plus py into y should be equal to m, and specifically this time we have px is 1, so we get x plus 2y is equal to 6. So maximize this utility subject to this constraint. So we take MRS first, that is so MRS. So what will be MRS? MRS, as we know, it is marginal utility of good x upon marginal utility of good y, which is equal to the change in the utility due to this. Okay, so I will not, you know it very well. So take the partial derivative with respect to x, we get 1. Partial derivative with respect to y, we get 1. So MRS is 1 this time. And what is the ratio of the prices? Okay, so optimal condition is we equate MRS with the slope of the budget line. Okay, so our MRS, and we have the ratio of the prices PX and PY. We equate these two, or let us see what happens. MRS came to be 1 and PX upon PY. PX is 1, PY is 2, so we have 1 upon 2. Here you can see slope of budget line, slope of indifference curve is greater than slope of budget line. And let us draw this case. So we have X, here we have Y. Let us draw the budget line, which is flatter this time. Okay, so we have this budget line. Then we have the indifference curve, which is steeper. So one indifference curve can be this indifference curve, another can be this, and that. So at this point we get the equilibrium. That means when y is equal to 0, we got corner solution, and to find out the units of good x, there the consumer will consume, plug y is equal to 0 in this equation, so we get x is equal to 6. Okay, so optimal bundle is at this, where we have 6 and 0 is the optimal bundle. Let us manipulate this time. Let us say price of good x is 2, price of good y is 1. So what happens? All other things are same. Okay, so we have this time 2x. This is our budget constant, this is our utility function. Again, find MRS. So that is the derivative of this function. So MRS, as we know, it is equal to 1. Now what is price ratio this time? Price of x upon price of y, which comes out to be here 2, because price of good x is 2, so 2 upon 1. Obviously here the budget line, so I am taking the second case here, this was first case. Here the slope of the budget line is greater than the slope of the indifference curve. So let us say we have x and y. Let us draw a steeper budget line. So budget line, and we have flatter indifference curve. Okay, so let us, so this is IC3. So in this case what happens? We get this point as optimal bundle. That means in this case we get x is equal to 0. In this equation, that means if x is equal to 0, y will be equal to 6, so optimal bundle will lie at this point. So we get 0 and 6 units. Okay, so third case can be when price of good x is 1, price of good y is also 1, so we have x plus y is equal to 6. So let us draw the third case, x and y. We have this budget line, and here MRS is same, which is 1, and this time px upon py, which is equal to 1 upon 1. So since slope of indifference curve and budget line is same, so we have this indifference curve or this. So our entire optimal bundles will lie on this budget line. Okay, so we will get many possible solutions, many optimal bundles. Okay, so how do we find out the optimal bundles? So let us solve it for 6 minus y. So when y is equal to 0, x will be equal to 6, so this will be one bundle. That means consumer will consume 0 units of good y and 6 units of good x. Let us plug y is equal to 1 in this equation. So if y is equal to 1, x will be equal to 6 minus 1, which is 5. So another can be 5 comma 1. Similarly, when y is equal to 2, x will be equal to 6 minus 2, which is 4. So another can be 4, 2, and similarly we will get many optimal bundles. Okay, this is how do we solve the utility maximization problem or constraint optimization problem when the consumer faces linear utility functions. We have the three cases we need to, and this is a little bit tricky because we need to equate, rather compare the slope of the indifference curve and the budget line. Why? Because we have linear indifference curve here. Let us take the third type of utility function, which is perfect complementary utility function. We will learn how the consumer chooses its optimal bundle when he maximizes his utility. Okay, so first, what is the general form? So general form for this kind of utility function is that is, let us suppose utility derived from the good x and y is equal to, which is equal to minimum of ax by. This is the general form. So utility derived from good x and y is equal to minimum of whatever is in the parenthesis, that is a times x comma b times y. X and y denote the goods, a and b are the constants here. Okay, so this perfect complementary utility function, we also call this Leontief utility. We also call it fixed proportion utility function. So our endeavor is to find out the consumer optimization. That means we want to maximize the utility of the consumer, which is equal to minimum of a times x comma b times y. And this consumer will be facing some budget constraint. Let us draw here, subject to the constraint, that is price of x times units of x plus price of good y times units of good y should be equal to the income of the consumer. Okay, so we want to maximize the utility subject to this budget constraint. Now what happens in case of fixed proportion utility function or Leontief utility function? Consumer consumes goods in a fixed proportion. Okay, so a simple example that we give is that, let us suppose a person goes to a shop and he buys a pair of shoes. Okay, so we are talking about a rational, or rather a healthy person who has two legs. Obviously we are not taking the case of the specially abled person, so we are taking the general case where a person has two legs. Okay, so when he goes to the shop, he purchases a pair of shoes, so left shoe and right shoe. Okay, so by purchasing this, let us suppose this consumer gets a utility of, let us say, 12. Now if this person chooses two left shoes and only one right shoe, again his utility will be same, because this extra left shoe will not give him additional utility. And in the same logic, if he chooses one left shoe and two right shoe, in this case also his utility will be constant, same what he was getting from one left shoe and one right shoe. But if he increases left shoe by 2, that means if he doubles the left shoe and doubles the right shoe, in this case his utility will change to, let us say, 24. So consumer's utility will only change when he increases the consumption of goods in a fixed proportion. That means if he doubles the units of good L, he has to double the units of good R to get more utility. Changing only one good without changing the another good will not yield any additional utility. That is the main essence of the Leontief utility function. Okay, So having said that, where will the consumer achieve its equilibrium? Okay, so for equilibrium or at equilibrium, what we do, we equate whatever is in our utility function in the parenthesis. That is, at equilibrium, consumer will choose AX is equal to B times Y. Okay, so this condition must hold at equilibrium. Solving for Y, so Y will be equal to A upon B X. Okay, graphically it is by, if I draw a simple graph here, we have X on the horizontal axis, Y on the vertical axis. So at equilibrium, what happens? The equilibrium bundle will lie where Y is equal to A upon Bx. That means this very line. This very line, you notice, Ax is equal to By. Ax is equal to By. Okay. So our optimal bundle will lie at that very point. Now, to find out the demand function or optimal bundle for good X and Y, so let us draw the budget constraint also here first. So let us suppose this is our budget line. Now at equilibrium, what happens? We plug Y is equal to A upon Bx into the budget line. So we have price of X times X plus price of Y times the value of Y is A upon Bx is equal to M. So let's take X common. We will be left with Px plus A Py upon B is equal to M. Solving further, so it becomes B times Px plus A times Py upon B is equal to M. Okay, so I am getting out of the limits here, so let me be within the limits. Okay, solving further, so X will be equal to, X is equal to, transpose it here, it becomes B times M divided by B Px plus A Py. Let us divide numerator and denominator by B. So X will be equal to, so B upon B is 1, so we are left with M. Here B upon B is 1, we are left with Px. So here it will become A upon B, P times Y. This is the optimal bundle of good, optimal choice of good X. Likewise, to find out the optimal choice of good Y, what will we do? We plug Y is equal to this stuff, or rather X is equal to this stuff in this equation. So Y will be equal to A upon B, the value of X is M divided by Px plus A upon By times the price of Y, good Y. So Y will be equal to, so it becomes AM divided by, so B into Px. So we have B into Px plus here B and B will get cancelled. We are left with A times Py. Divide both sides by A. Y star will be equal to M divided by B upon A times Px plus A and A gets cancelled. We are left with Py. This is the optimal choice of good X. Now, in this case, our indifference curves will be L-shaped, and our, let us say this is IC2. So the point where budget line and indifference curve, which is L-shaped in case of perfectly complementary utility function, optimal choice we will get an interior solution. So here we get X star, Y star. Okay, now why it is L-shaped, we will also discuss about that. Now we know that our optimal choice will lie at this dotted line. Below this, what happens? ax is greater than by, and here ax is less than by. Okay, so this below this dotted line is the region where ax is greater than by. Above this dotted region, ax is less than by. So here you can see, if we are at this point, let us say x star, and we are getting y star as the optimal choice. If I increase x, okay, without changing y, my utility will not increase, because we have to choose the bundles in a fixed proportion. If I increase x by, if I multiply x by 2, I have to multiply y by 2. So let me explain it here. So we have x and y here, and let us say we have this indifference curve. Let us suppose it gives us utility of 10, and at this point, let us suppose we are consuming, we have okay, let me write here L and R to explain it in case of left shoe and right shoe. So let us suppose here we have 1, L is equal to 1, R is equal to 1. So we are getting utility as 10 at this point. Now if I increase left shoe to 2 at this point, but I am not increasing right shoe, again I will be on the same point, my utility will not increase. Likewise, if I increase it to 3, I am still at this at this line. So because it is L-shaped, utility will remain same. Similarly, if I increase R to, let us suppose 2, without changing L, I will be again on this L-shaped line. So my utility will not change at all. Okay, so to understand it better, I will take a specific utility function here and solve it. Okay, so let us take a specific example. So let us say utility derived from two goods x and y is equal to minimum of x comma 2y. Okay, we have the budget for that. Let us suppose price of good x is 1, price of good y is equal to 2, and income of the consumer is 12. So we want to maximize the utility subject to the budget constraint, that is price of x times units of good x plus price of y times units of good y should be equal to the income of the consumer. Specifically px is 1, so we have x, plus py is 2, so we have 2 times y should be equal to 12. Okay, so at equilibrium what happens? At equilibrium x is equal to 2y, so we equate whatever is in the parenthesis in the utility function. So then we plug x is equal to 2y in this equation, so we have 2y plus 2y is equal to 12. 4y is equal to 12 implies y is equal to 3. So y is equal to 3, which means x will be equal to 6. So x is equal to 6. So we have optimal bundle as 6 comma 3, or let me write it here, x star y star is equal to 6 3. This is our optimal bundle. Now how do we show it on the graph? Let me draw a simple graph here. So we have good x on the horizontal axis, good y on the vertical axis. X is equal to 2y, so it will look like this. Okay, so this is our x is equal to 2y. This is our ray where our optimal bundle will lie. So we have a budget constraint, that is x plus 2y is equal to 12. If I draw it here, so when y is equal to 0, x is equal to 12. Let us suppose here it is 12, and when x is equal to 0, y will be equal to 12 upon 2, which is 6. Let us suppose it is here. So when I join, this is our budget line. Okay, now we got at this point our indifference curve which touches the budget line. So at this point we are getting 6 units of good x and 3 units of good y, which maximizes our utility. And let us see here whether it is true or not. So we have utility is a function of good x and y, which is equal to minimum of x comma 2y. Now let us see what is the utility derived. So when x is equal to 6, y is equal to 3, so we have minimum of x is 3, or rather x is 6, 2 times y is 3, so we are getting 6 is the utility here. Okay, u is equal to 6. Now if I increase x to 7, so let us suppose I increase x to from 6 to 7, so what will be our utility? So u will be equal to 7 3, which is minimum of, we have 7 times 2 into 3 again, so the minimum of 2 into 3 is 6 and 7 is again 6. So if I change it to 7, still I am getting a utility of 6. Likewise, if I increase, so I take these 6, the units of x, if I increase units of y from 3 to 4, so let us see. So we have minimum of x is 6, so we have 2 into y is 4 this time. So here you can see minimum of 6 and 8 is again 6. So I am at this point. Let us suppose it is 4. Again I am on the same indifference curve. Okay, so my utility does not increase. So consumer will always choose to consume at this kink point. Okay, that's why we are calling it a fixed proportion utility function, where a consumer consumes goods in a fixed proportion. We also call this Leontief utility function. So that's it. We will learn about the Walrasian equilibrium and Marshallian equilibrium using the supply and demand functions. The question is, suppose that demand and supply functions in a market are given as quantity demanded is equal to 100 minus P and quantity supplied is equal to 200 minus 5P. We have to analyze whether the equilibrium is Walrasian stable or Marshallian stable. Okay, so let me draw a simple graph here. Okay, so we have quantity on the horizontal axis, price on the vertical axis. Okay, we are being given the demand function, that is quantity demanded is equal to 100 minus P and quantity supplied is equal to 200 minus 5P. Okay, we have unusual supply function here, you can see, and I will explain here. Let me first draw the graph of the demand function. Okay, so if I draw the graph of Q is equal to 100 minus P, so how do we draw the graph? Let us suppose when P is equal to 0, in this case implies Q will be equal to 100. Okay, so let us suppose this is here 100. Okay, P is equal to 0, and when Q is equal to 0 in this equation, P will be equal to 100. Okay, so price is equal to 100. Let me show it here, or let me draw. So we have this demand function. So usual demand function we have. Now what about supply function? Let me draw the supply function also. When Q is equal to 0, when Q is equal to 0 in this equation, that means 200 minus 5P is equal to 0, or 5P is equal to 200, or P is equal to 200 upon 5. So P will be equal to 5 ones are 5 4s are, so we get P is equal to 40 here. And let me draw it here. So P is equal to 40. Let us suppose it is here, it is 40. And similarly, when we plug P is equal to 0, Q will be equal to 200. Okay, so when P is equal to 0, Q will be equal to 200. I will not be showing this because I have to explain other stuff here. So we will have this kind of supply function. Okay, here this intercept is 200. Now what is the equilibrium here? Then we will explain the Marshallian and Walrasian. So stability. So we know that at equilibrium, what happens at equilibrium? At equilibrium, demand is equal to supply. So this is our demand function. That means 100 minus P is equal to, what is supply? Supply is 200 minus 5P, 200 minus 5P. Let us solve it for P. Transpose this term here and this term there. So we will get minus P. Transpose it here, it becomes plus 5P is equal to, we have 200. When I transpose it, it gets subtracted. So we get 4P is equal to 100. Dividing both sides by 4 implies P will be equal to 4. So 100 upon 4 is 25. So initially we get, okay, so P is equal to 25. So let me write it here. So at equilibrium we get 25. And what about quantity? Plug P is equal to 25 in either demand or supply function. So let us put it into the demand function. So Q will be equal to 100 minus 25. So quantity demanded will be equal to 75. So let us suppose this point is 75. Okay, so it is here Q. Here we have this P initially. So we got equilibrium, price and quantity. Now we need to discuss about the stability of this very equilibrium. Okay, using the Walrasian approach and Marshallian approach. Okay, so let us first take the Walrasian case. Now Walrasian approach talks about price adjustment. Okay, price adjustment, and I will be explaining it here. So let me first explain what is meant by equilibrium. Now by equilibrium we mean, equilibrium refers to a position of rest or balance. Okay, so at this point we have a rest or balance. So we get in demand and supply, we mean where supply and demand functions intersect, that very point is called the equilibrium point. Okay, so simply it refers to a position of rest or balance. So demand and supplies are balanced at this point, so this is equilibrium. Now what about stable equilibrium and unstable equilibrium? Okay, let me explain it with an example. Let us suppose I have this bowl, and in this bowl, let us suppose I have this ball at this bottom. So I am saying that this ball is at equilibrium. It is at rest, at balance. Okay, so this is equilibrium. Now suppose if there is some disturbance to this ball. Okay, if I move this ball once, so it will reach first here. Okay, then it will go here, and then there will be adjustments. It will go here, then here, and finally it will reach to its original position. So in this case we say the equilibrium is stable, because when there was external force or when there were some forces that tried to deviate or disturb this equilibrium, there were the market forces that helped it to reach to its original position. So we say it is equilibrium stable. Okay, stable equilibrium. So this is stable equilibrium. Now what about unstable equilibrium? So let me draw this bowl again, but upside down. If I have a ball on this here at the top, now if this ball is disturbed once, so it will either go downwards here or it will go downwards here, but it will not be able to reach to its original position. Okay, so we say this equilibrium is unstable. Initially it is an equilibrium because it is at rest, it is at balance, but when this balance or rest is disturbed, we are not able to get it back to the original position, so we say it is unstable equilibrium. Okay, that means once equilibrium is disturbed, market forces tend to move it further away from that very equilibrium, so we will not be able to reach to the initial point. Okay, now there are two approaches of seeing the stability and instability. That is, first is Marshallian approach. Okay, so Marshallian approach, works in the price adjustments. Okay, let us suppose price changes. Okay, in this case, let me show it here. Let us suppose by some reason, initially we were at Q. Let us suppose price increases by some reason to P1. Okay, P1. Now at P1, so let me write it here. If price increases to P1, what happens here? You can see this is our supply function, this is our demand function. So here demand is more, supply is less. Okay, what happens at this point at P1? Demand is more. Okay, so demand is greater than supply. Okay, in this case demand is greater than supply. Now what happens then? We have the excess demand. If we have the excess demand, what will happen? Firms will charge higher price. Firms will charge higher price. Let us say P2. Okay, let us suppose we have this P2. So what happens? Initially we were at this point, so when the equilibrium was disturbed, we reached here. Okay, but when reaching at this point or this point, there are forces in the market that moves this price in this direction. Okay, so we are not able to reach back to the initial point. Why? Simply at P1, what happens? We have demand is more than supply. When demand is more than supply, firms will charge higher price. That means we are moving to upward direction. We are not going back to the initial direction. Okay, so when firms charge higher price will increase. Okay, that means this equilibrium is unstable. Okay, so it is unstable. And same is the case when if price is at this point. Okay, let us suppose price decreases by some reason to P2. Okay, so let us suppose we are at this point. P2. What happens at P2? Here you can see, here supply is greater than demand. Okay, so here you can see red denotes the supply, this is demand. So at P2 we have supply is greater than demand. Okay, so what will happen here? Since supply is greater than demand, firms will charge less price. Okay, they will decrease the price. So price will decrease. If price decreases, we are moving to this direction. So let us suppose P3. So we are going further away from this initial equilibrium. So we say it is unstable in case of Walrasian. But what about Marshallian approach? So we see that Walrasian approach works through price adjustments when price is disturbed at P1. So we are moving away from the initial equilibrium to P2, P3 and so on. So we are not going to initial position of P, which would have given us the stable equilibrium. Now let us see the Marshallian. Okay, so let me be very specific here and let me draw another graph. Again this graph. So we have quantity here, price here. Okay, so we have, this is our demand function. Okay, and let me draw the supply function. Okay, this is our supply function. Initially we were at this point Q. Okay, now let us take the Marshallian approach. Marshallian approach. So Marshallian approach works through quantity adjustment. Quantity adjustment. Okay, so again take this example. So let us suppose by some reason we were at this point, let us at Q. Okay, let us suppose quantity increases to Q1. Okay, Q1. So let us suppose Q1 quantity decreases to Q1. Okay, at Q1 what happens? We have what we call supply price is greater than demand price. Okay, so let me write it here. So supply price is greater than demand price, or we can say we have excess supply price. Okay, when we have the excess supply price, consumers are not willing to pay more price than being charged by the suppliers. This will induce suppliers or producers to decrease the price. Okay, since supply price is greater than demand price, here you can see consumers are not willing to pay more price than being charged. Okay, since price are being charged at this point, but demand is only consumers are seeing it at this price. Okay, so there is no willingness to pay higher price by the consumers. This will induce producers to decrease price. Okay, implies price will, or rather this will induce producers to decrease supply. That means they will decrease the quantity. So if they decrease the quantity, initially we were at this point, so we will be going in this direction, because here quantity is more when willingness to pay by the consumers is less than the price they are being charged. So suppliers will decrease the quantity. When they decrease the quantity, let us suppose we are at this Q2. Okay, so we are reaching at this point, we are reaching to the direction of the equilibrium, and this adjustment will continue till we reach Q, which was our initial equilibrium. Okay, so let me explain it again, because I was not able to draw the graph smoothly. Okay, so let us suppose this is our demand function, this is our supply function. Okay, initially we were at this point Q. Okay, let us suppose quantity decreases due to some reasons to Q1. At Q1, what is demand price, supply price is more than demand price. Okay, we have excess supply price here. That means consumers are not willing to pay more price than being charged by the producers. This will induce producers to decrease the supply. So supply will decrease, let us say to Q2. Okay, since we were at this point, we moved to Q1 by some reason, then we moved back to Q2, and this adjustment will continue till we reach back to the initial point. So we can say that in this example, numerical example, it is Marshallian stable. Marshallian stable. Okay, actually I have made the stability condition in case of Walrasian and Marshallian in detail. You can check out that very video also, but it was only to explain this numerical. The question is, a producer desires to minimize the cost of production. C is equal to 4K plus 2L. where K and L denote the units of labor and capital employed respectively, subject to the production function Q is equal to 8 times K to the power 1 upon 2 times L to the power 1 upon 4. Find the equilibrium combination of capital and labor in order to minimize the cost of production when the output level is 60 units. Okay, so this is a case of cost minimization. So our endeavor is to minimize C, which is cost, which is equal to 4. 4 denotes the price of capital, plus 2 denotes the price of labor, that is the wage rate. So we want to minimize the cost subject to the production constant that we are facing, that is 8 K to the power 1 upon 2 times L to the power 1 upon 4, and it should be equal to Q, and we have the production constant, that is we want to produce 60 units of output. Okay, so the question is we want to minimize the cost to produce 60 units of output when we have this production function. So there are two ways to solve this question. First is the Lagrangian multiplier method, and another is the tangency condition. Let us first solve it using Lagrangian multiplier method. So for that, what we need to do, we need to to solve it using Lagrangian multiplier method, we set the production constant, this equation equal to 0. That means we have 60 minus 8 K to the power 1 upon 2 times L to the power 1 upon 4. We set it equal to 0. Okay, first step is this. Second step is we multiply this resulting constant both sides by lambda. Okay, so lambda times 0 will be 0 on the right hand side. I will not write it. Now then the third step is we form the Lagrangian function, which is equal to the objective function, which is our cost function, and the resulting constant that we have formed. So it will be equal to 4K plus 2L plus this equation, lambda times uh, 60 minus 8 K to the power 1 upon 2 times L to the power 1 upon 4. This is our Lagrangian function. Okay, to find out the optimal combination of capital, labor and lambda. So lambda denotes the shadow price. I will not explain the lambda here. So since our endeavor is to find out the optimal combination of capital and labor, we will concentrate on that very thing. So to find out the optimal values of K, L and lambda, we differentiate this Lagrangian function partially with respect to capital, labor and lambda and set them equal to 0 simultaneously. So let us see. So L subscript L. Okay, so let me write. Let us say it denotes the partial derivative of this function with respect to L. So derivative of a constant is, since we are taking partial with respect to L, derivative of first term is 0 because here we have K. Derivative of the second term is 1. We are left with 2 because the derivative of L is 1. Then we have here plus this term. So the derivative of 60, it is constant, it is derivative 0. Now we need to find out the derivative of L here. So the exponent of L becomes coefficient. So we have and we have minus obviously. So we have minus, then we have lambda, then we have the exponent of L is 1 upon 4, which becomes coefficient. Then we have 8 K to the power 1 upon 2, it remains same, and the exponent of L is subtracted by 1. So 1 upon 4 minus 1 is equal to, so it is 1 minus 4, which is minus 3 upon 4. Okay, and we set it equal to 0. Likewise, we take the derivative with respect to K partially. So differentiating partially with respect to K, derivative of K is 1. We are left with 4. Then we have minus, then we have lambda, and we partially differentiate this with respect to K this time. Okay, so the exponent becomes coefficient. So we have 8 times 1 upon 2 K to the power, exponent is subtracted by 1, so it becomes minus 1 upon 2 L raised power 4, L raised power 1 upon 4 remains the same because we are taking partials with respect to K this time, and we set it equal to 0. Okay, so let us take only these two. These are suffice to find out the value of capital and labor here. Okay, So we do one thing here. Since this term is equal to 0, this term is also equal to 0, can we rewrite these two as? Why do I write? I don't have the space here, so let me rewrite these two equations. So can I write 2 is equal to lambda, so 4 ones are 4 twos are, I get here 2 k to the power 1 upon 2 L to the power minus 3 upon 4, and if I rewrite it, it will become 4 is equal to, so here 2 ones are 2 fours are, here we will get 4 k to the power minus 1 upon 2 L to the power 1 upon 4. Okay, then what will we do? Let us say this is equation first, this is equation second. We divide equation first with equation second. Okay, so to save the space, I divide them here. I divide it here. So 2 upon 4 is 1 upon 2 is equal to lambda get cancel. So 2 ones are 2 twos are, here we get 1 upon 2. Transpose this k to numerator, it will get multiplied, so it will become k to the power 1 upon 2. Transpose it here, it gets multiplied, but exponent sign changes, it is minus upon 1 upon 2, it becomes plus 1 upon 2. Okay, in the same way we have L raised power 1 upon 4 here. Transpose this term here, it gets multiplied, but exponential sign changes. So these are the basic things, so it becomes plus 3 upon 4. Bases are same, we can add the exponent, so it becomes k 1 upon 2 plus 1 upon 2, and in the denominator again bases are same, we have 1 upon 4 plus 3 upon 4, which is equal to, so 1 half plus 1 half is 1, and here 1 upon 4 plus 3 upon 4 is 4 upon 4, which is L. Okay, so we got here k upon L when I solve this very much. Okay, I guess. So this 1 upon 2 gets cancelled on both sides, which implies k will be equal to L. Now we plug k is equal to L into the production constraint. Okay, so we have 8 in place of k I write L, so we have L raised power 1 upon 2, then we have L raised power 1 upon 4 is equal to 60. So again bases are same, we can add the exponent, so we have 8. So 1 upon 2 plus 1 upon 4 becomes 4 plus 2 divided by 8, so it becomes 10 divided by 6 divided by 8. So I'm really sorry for this slow calculation. So we have 4 plus 2 is 6, and 2 4s are 8, 6 upon 8, which is equal to 2 3s are 2 4s are, so we get 3 upon 4. Okay, so L raised power 3 upon 4 is equal to 60, which gives us L raised power 3 upon 4 is equal to 60 divided by 8, or L is equal to, transpose it here, it becomes 60 divided by 8. So let us see what is 60 divided by 8 first. So 60 divided by 8 is equal to, so 2 30s are 2 4s are, okay, then we have 2 15s are 2 2s are, so 15 divided by 2, 15 divided by 2, when I transpose it becomes 4 upon 3. Okay, so L will be equal to 15 divided by 2 raised power 4 upon 3. This will be the optimal choice of labor employed to minimize the cost. To find out the value of k, plug k is equal to L in this equation. So since k is equal to L, that means k will be equal to, k is equal to again 15 upon 2 raised power 4 upon 3. So L star k star, that is optimal combination choice, will be 15 upon 2 4 upon 3 and 15 upon 2 4 upon 3. Okay, this will be our optimal choice. I hope I have done the calculation correctly. Okay, so This should be the answer. Now let us solve it by another method, or rather what we call the tangency condition. Okay, so for that what we need to do, let us rub this out, and to see whether we have done it correctly or not, we check it using tangency condition. So for that what we do, let us draw the graph to make the things clear. So if I draw the graph here, a simple graph, we have the labor on the horizontal axis, units of capital on the vertical axis. We have the production constraint. Okay, so this is our ISO count. Okay, with the given ISO count we want to minimize the cost. Okay, let us say this is our one ISO cost line. Okay, so another can be this one, then we have another. Okay, so the consumer's endeavor is to minimize the cost subject to the given production constraint. Okay, so the optimal choice will not be, let us say this is IC1, IC2, and this is IC, rather we don't have the indifference curve here, we have ISO count. Let us say IQ1, IQ2, and IQ3. Okay, now which of these will give us the optimal choice? Optimal choice will lie at a point where the ISO count and ISO cost lines are tangent to each other. So this point will give us the optimal combination. This point satisfies a condition where the marginal rate of technical substitution between labor and capital is equal to the input prices, that is price of labor upon price of capital. Okay, now using tangency condition, our equilibrium will be at a point where marginal rate of technical substitution between labor and capital is equal to ratio of the prices, that is price of labor upon price of capital. Now what is price of labor? Price of labor is 2, price of capital is 4. Okay, marginal rate of technical substitution is simply the ratio of the marginal product of labor and marginal product of capital, and it should be equal to PL upon PK is 2 upon 4. So MPL is simply the change in the output due to the change in the units of labor employed. MPK is the change in the output due to the change in the units of capital employed, and it should be equal to 2 upon 4, which is equal to 1 upon 2. Okay, now the partial derivative of production function, this production function with respect to labor. Okay, so we need to partially differentiate this with respect to labor. So the exponent of L becomes coefficient, so we have 1 upon 4, then we have 8, then we have k to the power 1 upon 2. It remains the same because we are taking partial with respect to L, but the exponent of L gets subtracted, so 1 upon 4 minus 1 is minus 3 upon 4. Likewise, we take partial with respect to k, so exponent of k becomes coefficient, then we have 8, k to the power, exponent is subtracted by 1, it becomes 1 upon 2, and L to the power 1 upon 4 remains the same because we are taking partial with respect to capital. Should be equal to 1 upon 2. So 8 and 8 gets cancelled. We are left here 1 upon 4 into transpose here, it becomes 2 upon 1. Again transpose this to numerator and this to denominator, it will become k upon L is equal to 1 upon 2. So here we have 2 upon 4, k upon L is equal to 1 upon 2. So 2 upon 4 is basically rather 1 upon 2. So 1 upon 2 and 1 upon 2 will get again cancelled. So k upon L is equal to 1, which implies k is equal to L. Now plug k is equal to L into the production constant. So we have 8 times, in place of k we write L raised power 1 upon 2, and in place of L we have L raised power 1 upon 4, same, is equal to 60. Again we have 8, so 1 upon 2 plus 1 upon 4, 1 upon 2 plus 1 upon 4, so 6 divided by 8, so it becomes L raised power 6 divided by 8 is equal to 60, or L raised power, so this is 2 3s are 2 4s are is equal to 60 divided by 8, which is equal to 15 divided by 2. So L will be equal to, transposing the exponent gets reciprocated, Okay, so we have 15 upon 2. If it is here 3 upon 4, it becomes 4 upon 3. And this is the optimal units of labor employed. So K will be equal to L since they are equal. So we have 15 upon 2 raised power 4 upon 3. That will be the units of capital employed to minimize the. So we will solve an interesting question on elasticity. The question is the demand function Q1 is equal to 50 minus P intersects another linear demand function Q2 at P is equal to 10. The elasticity of demand for Q2 is 6 times larger than that of Q1 at that point where P is equal to 10. The demand function for Q2 is, options are being given, we need to find out the correct option. Okay, so we are being given the demand function, that is Q1 is equal to 50 minus P. Okay, we have another demand function that we are supposed to find out, that is we need to find out the demand function for Q2. Okay, and what will be the demand function look like? It will be like this A minus B times B. Okay, so we need to construct this kind of demand function. We need to find out the value of A. Further, we are being told that P is equal to 10 where Q1 and Q2, the demand function is intersect with each other. Also, we are being told that the elasticity of demand for Q2 is 6 times larger than that of Q1. That is, let us denote the elasticity of demand of Q1 by E1. It is rather the elasticity of demand for Q2 by E2. It is equal to, it is 6 times larger, that means 6 times the elasticity of demand for Q1. That is being given us. So let me try to draw a simple graph here to explain, and let me see if I am within the limits also. Okay, so we have quantity Q on the horizontal axis, P on the vertical axis, that is price. Elasticity of demand of Q2 is 6 times greater than Q1. They intersect with each other. Okay, so let me draw the two demand functions. Let us say this is one demand function. We have another demand function, that is elasticity of demand for Q2 is 6 times greater than that of Q1. Let us say this is demand function for good Q1 and this is demand function for good, or let us suppose it is demand function for good Q2 and this is demand function for good Q1. So these two demand functions intersect at a price of $10. Okay, so what will be the quantity demanded for Q1 and Q2, because they intersect each other? So Q1 will be equal to Q2, which we need to find out. So let us first find out the Q1. So quantity demanded of good Q1 will be equal to 50 minus the price at that very point, that is 10, so which is equal to 40. So Q1 is equal to 40, which is equal to Q2 here, because they both intersect at that very point. Now we know that elasticity of demand for good Q2 will be equal to the change in the quantity demanded of good 2 divided by the change in the price into P price divided by quantity demanded at that very price of good 2, and it is equal to 6 times. So we have 6 times what is the elasticity of demand for good Q1, that is the derivative of this function, that is the change in the quantity demanded of good 1 due to the change in the price of good 1 into price upon quantity demanded of good 1 here. Okay, so dQ2 upon dP, we are supposed to find out price is being given us as 10, so we have 10, quantity demand of good 2 is 40, is equal to 6 times, now dQ upon dP means the derivative of this function with respect to price, derivative of P is 1, so we write here minus 1 into price is 10 and quantity demanded is 40. Okay, so we have this relationship here. So this 0 0 gets cancelled, 0 0 gets cancelled. We have 2 2s are 4, 2 3s are 6. Okay, okay, I am within the limits. So we have dQ2 upon dp is equal to so here we have 4 also into 1 upon 4 is equal to minus 3 upon 2. Okay, solving further. So we have dq2 divided by dp into 1 upon 4 is equal to minus 3 upon 2. Okay, now let us transpose this dp here, so we get 1 upon 4 dq is equal to minus 3 upon 2 dp. Okay, now what will we do? We take the integral on both sides. That means we have 1 upon 4, the integral of dq is q, plus we add the constant of integration will be equal to, here we have minus 3 upon 2, and the integral of dp is p, and we add the constant of integration. Okay, so let us say it is c2. Now we can do one thing here. So we have c2, transpose this here, so we have 1 upon 4 q, so we have q2 here. Okay, let me be specific with the subscript is q2, then transpose it here, it becomes 3 upon 2 p is equal to c2 minus c1. Okay, so which is equal to, we have 1 upon 4. Now we know that q2 is equal to 40, so let us write it here 40 plus 3 upon 2 times 10 is equal to c2 minus c1. So it becomes here 4 ones are 4, 10s are 40, so we have 40, 2 ones are 2, 5s are 10, 5 3s are 15, so we get here, sorry, here we get only 10, 4 ones are 4, 10s are 40, so here we have 15 is equal to c2 minus c1, or c2 minus c1 is equal to 25. Okay, now we plug this value c2 minus c1 is equal to 25 in this equation. So we have 1 upon 4 q2 plus 3 upon 2 p is equal to, so c2 minus c1 is 25, which implies we have 1 upon 4 q2 is equal to 25 minus, transpose it here, it becomes minus 3 upon 2 p, or q2 will be equal to, transpose this 4, it gets multiplied, so we have 4 into 25 which is equal to 100 minus, so transpose this 4 here, so we have 2 ones are 2, 2s are 4, so 2 3s are 6, so we get 6 times p. So we have this demand function q2 is equal to a minus bp, so in place of a we have 100 minus b is 6 times p, so the correct option should be q2 will be equal to this very function, that is the demand function for q2. We will learn about the Young's theorem. Okay, so its formal statement is, if the mixed partial derivatives of a function are continuous, then they are equal. Okay, so let me explain it. Young's theorem is also called the Clairaut's theorem, or symmetry of the second derivative. It simply tells us, if we have a continuous function, and if I write it here, let us suppose we have f of xy is a continuous function. Okay, continuous function, then the mixed partial derivatives of this continuous function are equal. That is to say, that is, if I take the cross partials of this function, that is d square f of xy upon dx dy is in fact equal to d square f of xy divided by dy dx. This is the statement, and I will explain it with an example. Very simple example. Let us suppose we have a function f of xy is equal to 2x cube, let us suppose 2x cube y plus 5 x y square plus 5. If since this is a continuous function, now it is second order cross partials are equal according to the Young's theorem. That is, if I take the second order cross partials or mixed partials, they will be equal. And let us prove that here given this function, and let us suppose whether the Young's theorem holds here or not. So to find out the second partial, first we need to find out the first partial rather. So let us take del f of x y. So let us differentiate this with respect to x, that is partially del x. So partially differentiating with respect to x, so the exponent of x becomes coefficient. So we have 3 2s are 6, x and exponent is subtracted by y 1, so we get 6x square times y, plus here the derivative of x is 1, so we are left with 5 y square, and the derivative of a constant is 0. Okay, likewise we take, now let's take it as second derivative with respect to x, that is d square f of xy upon del x del y. This time we take the derivative second cross partial derivative with respect to y. So since this is df xy upon del x, now its derivative with respect to y, we need to differentiate it again with respect to y. The derivative of y is 1, so we are left with 6x square plus derivative of y square is 2y, so 2 into 5 is 10y. Okay, in the same manner, let us take the derivative of this function with respect to y first, that is del f of xy upon del y. So let us first take with respect to y. So derivative of y is 1, so we are left with 2x cube plus derivative of y square is 2y, so 2 5s are 10xy. Now let's take the derivative with respect to x of this function. So we have del f of xy upon del y del x. So we have 2 3s are 6x plus derivative of x is 1, so we are left with 10y. Okay, so 3 2s are 6x square here. Okay, here you can see this del square f of xy upon del x del y is in fact equal to del f of xy upon del y del x, because we got the same result from 1 and 2. We can derive or deduce that the second order cross partials are equal according to Young's theorem. Okay, so don't get confused or get scared by these symbols. So if I write another function, and let me use the subscript symbols for partial derivatives. For that, let me take another function. Let us suppose I have a function f of xy is equal to 2x square y plus 3y x. Okay, so I have taken a random function which is continuous. This can be if I take the simple what we do, the subscript notation of the partial derivatives. Let us first according to the Young's theorem, what should happen if we have f of x y, if it is continuous, that means f of x y should be equal to f of yx. Okay, the second order cross partials are equal. Okay, and let us see whether this holds or not. So let us partially differentiate with respect to x first, this function. So derivative of x square is 2x, so 2 into 2 is 4xy plus derivative here of x is 1, so we are left with 3y. Okay, now let us take it as cross partial with respect to x. So we have f of f subscript xy, that means the derivative of this function with respect to y, derivative of y is 1, so we are left with 4x plus derivative of y is 1, so we are left with 3. Okay, so this is one result. Now let us take with respect to y the partials. Okay, f of y is equal to derivative of y is 1, so we are left with 2x square plus derivative of y is 1 here, so we are left with 3x. Now let us take f of cross partial with respect to x. So this is fy, so fyx means the derivative of this function with respect to x. Derivative of x square is 2x, so 2 into 2 is 4x, and derivative of x is 1, so we are left with 3. And here you can see we got 4x plus 3, 4x plus 3, which implies f of xy is equal to f of yx. Okay, that means the second order cross partials are equal according to Young's theorem if a function is continuous. So the question is, given consumption is equal to 250 plus 0.25 y subscript d, where yd denotes the disposable income, autonomous investment is 100, government spending which is autonomous which is 50, and marginal tax rate is 20% of the income. Okay, so 20% is the tax rate. We need to find out the equilibrium level of consumption in this case. Okay, now to find out the equilibrium level of consumption, first we need to find out the equilibrium level of income, and we know that our y total income is equal to consumption expenditure plus investment expenditure plus government spending. Okay, so total income will be equal to, so consumption function is 250 plus 0.25. so what is yd? Y subscript d means disposable income, which is equal to our total income minus the tax rate that is paid on that very income, so that is equal to y minus ty. Okay, so in place of yd, I can write y minus t is 20%, which is 0.2 y. Okay, plus we have the investment which is autonomous which is 100, plus the government expenditure which is autonomous here, which is 50 here. Okay, solving further, so we have 250 which is 350, which becomes 400. Okay, so we have y is equal to 250 plus 100 is 350, then we have 50 which becomes 400, plus we have 0.25, so y minus 0.2y is 0.8y. Our income will be equal to 4, that is our y is equal to 400 plus, now what is 0.25 times 0.8, so we have 0.25 into 0.8, so it becomes 8 5s are 40, 8 2s are 16, plus 4 is, so we have 1 2 and 3, 1 2 and 3, so here we have the decimal. Okay, so we have 0.2 y. Okay, now we transpose it here, we get a subtracted y minus 0.2y is equal to 400, which implies subtracting 0.2y from y, we get 0.8 y is equal to 400, or y is equal to, so 0.8 is 8 upon 10, so it becomes 400 into 10 divided by 8, so we have 8 1s are 8 5s are 40, so we have 50 times 100 which is 500. 500 is our equilibrium level of income, but we are supposed to find out the equilibrium level of consumption. Okay, so our consumption will be equal to, so C is equal to, so we have 250 here plus 0.25 can be written as 1 upon 4. Then we have, in case of y, yd, we have y which we got 500 minus tax rate is 0.2, so 0.2 times y which is 500. Okay, so we have C will be equal to 250 plus 1 upon 4, so we have 500. Now 0.2 of 500 is 22 divided by 10 into 500, so you rubber sawal, so 50 into 2 is 100, so we get here 100, so C will be equal to 250 plus 1 upon 4, 500 minus 100 is 400, so we have 400, so 4 1s are 4, 100s are, so C will be equal to 250 plus 100, which is C will be equal to 350. That will be the equilibrium level of consumption. The question is, consider the production function, that is Q, which is output, which is the function of capital and labor, which is equal to 2 under root K plus 3 under root L whole square, If n subscript k and n subscript l denote output elasticities with respect to capital and labor, then find the sum of output elasticity of capital and output elasticity of labor. Options are 2, 1, 0.5 and 4. Okay. So how do we solve this question? So we need to find out nk and nl. Now let us first find out the nk, that is output elasticity of capital. That will be equal to the change in the output due to the change in the units of capital employed times k divided by the output. Okay, this will be an output elasticity of capital. Likewise, n subscript l means the change in the output due to the change in the units of labor employed into L upon Q. Then we need to find out the n subscript k plus n subscript l, that is the sum of these output elasticity of labor and capital. Okay, so how do we find it? Let us see here. So first we need to find out this term dq upon dk. So we have this production function, that is q is equal to twice, in place of k, can I write it k raised power 1 upon 2, plus then we have thrice l raised power 1 upon 2 whole square. Okay, so first we need to find out this dq upon dk, that is the partial derivative of production function with respect to capital. Okay, if I partially differentiate it with respect to k, first we apply the power function rule, exponent becomes coefficient, so this 2 comes here. Then we have twice k raised power 1 upon 2 plus 3 l raised power 1 upon 2, and exponent is subtracted by 1, so it becomes 2 minus 1, which is 1. We don't write it. Times we apply the chain rule, the derivative of this 2 k raised power 1 upon 2. Here we have to apply, because we applied power function rule, then we need to internally differentiate with respect to k. Okay, now we have 2 k raised power 1 upon 2, so first we have 2, the derivative of k raised power 1 upon 2 will be, so again 1 upon 2 becomes coefficient, so we have 1 upon 2, and exponent of k is subtracted by 1, so it becomes 1 upon 2 minus 1 is negative 1 upon 2. Okay, and this is our dq upon dk. So here what happens, this 2 and 2 gets cancelled, so dq upon dk is this term, and to this we multiply k upon q. So let me write it here now. So here we have, so we got dq upon dk came out to be twice 2k, or let me write it here to make sense. Now dq upon dk, del q upon del k into k upon q will be equal to, so del q upon del k is this term, that is 2 times twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 times k raised power negative 1 upon 2. So this is this derivative times this term, that is k upon q. So we have into k, and what is q? Q is this term. Okay, we divided by this twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 whole square. Okay, so here you can see we have 2 terms here, one term will get cancelled with this, so we will be left with, and here k raised power minus 1 upon 2 times k, so we have the same exponent, so 1 upon 2 plus 1 becomes 1 upon 2. Okay, so we have k raised power negative 1 upon 2 times k raised power 1, it becomes k raised power negative 1 upon 2 plus 1, because we have the same exponent, so we have same basis, we can add the exponents here. So we have k raised power, so it becomes negative 1 plus 2 divided by 2, which becomes k raised power 1 upon 2. Okay, so when we multiply these two, it becomes k raised power 1 upon 2. And let me write it here. So we got twice. So this term vanishes, this gets cancelled, so we are left with twice k raised power 1 upon 2 divided by one term we are left with here, k raised power 1 upon 2 plus 3 l raised power 1 upon 2 whole square. Okay, this is this n subscript k, that is output elasticity with respect to capital. Okay, so let me write it here. So n subscript k came out to be, do I have the space? Oh, okay, so n subscript k came out to be twice k raised power 1 upon 2 divided by, okay, I have the space, so twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 whole square. Okay, so this is n subscript k. So this term, to this we need to add n subscript l, and we need to find out that very thing. For that, let me rub this out again. Now this time we differentiate dq upon dl with respect to l, this partially. So dq upon dl, dq upon dl will be the partial derivative of this function with respect to l. So again exponent becomes coefficient first, so we have then twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2, and exponent is subtracted by 1. Then we multiply it with the partial derivative which is in the parenthesis with respect to labor. Okay, this time again we have first 3, exponent becomes coefficient, we have 1 upon 2, and exponent is subtracted by 1, it becomes negative 1 upon 2. So this is our dq upon dl. But we are supposed to find out dq upon dl into l upon q. Okay, so this is dq upon dl, this term. To this we multiply by l upon q. So we have into l upon q is this term again, so we have divided by twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 whole square. Okay, so here one term will get cancelled, we will be left with, so that is dq upon dl l upon q. It comes out to be here this 2 and this 2 gets cancelled, so we are left with 3 times again we have the same basis, we can add up the exponents, it becomes l raised power 1 upon 2, and we have this term in the denominator, that is twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 whole square. Okay, this is our n subscript l. Now since we need to add this, so n subscript k is this term, n subscript l is this term, so we have thrice l raised power 1 upon 2 divided by twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2 whole square. Here you can see we have the same denominator, then we can add up the numerator. So we have twice k raised power 1 upon 2 plus thrice l raised power 1 upon 2, and in the, sorry, we don't have the square here, because one term gets cancelled. So in the denominator we have twice k raised power 1 upon 2 plus 3 l raised power 1 upon 2. Okay, so here you can see the sum of output elasticity with respect to capital and labor will be equal to, so this term gets cancelled with this term, so we are left with 1. So the output elasticity with respect to capital and labor, when we add them, comes out to be 1 in this case. So we will learn the impact of the per unit taxes in case of monopoly. The question is, consider a monopoly with demand function P is equal to 90 minus 10x, P is the price, x is the output, and cost function, which is total cost, is equal to 10 times x. We need to find out the profit maximizing price and output. Now suppose government imposes a per unit tax which is T is equal to 20 find the new price and output after the imposition of per unit x. Okay, so let us solve it. We have the demand function, that is P is equal to 90 minus 10x. This is our inverse demand function, and for the sake of simplicity, let me draw the graph here to make things clear. So we have the output on the horizontal axis, price on the vertical axis. If I plot this demand function, average revenue function, what we call also, on this graph, so what will happen? So when x is equal to 0, P will be 90. So when x is equal to 0 in this equation, so P will be equal to 90. So we have 90 here. Okay, and when P is equal to 0, when P is equal to 0 in this equation, so 90 minus 10x is equal to 0, or 10x is equal to 90, or x is equal to 9. Okay, here we have 9, let us suppose. So let us join these two. This will be our average revenue function. Okay, or this is our demand function. Also, we are being told that cost is equal to 10x. Before the imposition of per unit tax, what will be the profit maximizing condition for monopoly? That will be marginal revenue should be equal to the marginal cost. So we need to find out the marginal revenue and marginal cost first. Okay, so as we know, to find our marginal revenue, first we need to find out the total revenue, which is price into output, which will be equal to, so P is 90 minus 10x, to this we multiply by x. So total revenue will be equal to 90x minus 10x square. Marginal revenue, as you know, it is simply the derivative of the total revenue function with respect to x. Derivative of x in the first term is 1, so we are left with 90, minus derivative of x square in the second term is 2x, so 2 into 10 is 20x. Okay, sorry, we are calculating marginal revenue. I have written marginal cost. Likewise, we need to find out the marginal cost. Marginal cost is simply the derivative of cost function with respect to x. Derivative of x in this term is 1, so we are left with 10. Okay, so for profit maximization, we equate marginal revenue with marginal cost. And what will be the marginal cost is equal to 10? Let us draw it on this diagram. So let us suppose this is our marginal cost. Okay, MC before the imposition of tax. For profit maximization, we equate marginal revenue with marginal cost. This is our marginal revenue, this is our marginal cost. That means 90 minus 20x should be equal to 10. Solving further, so 20x is equal to 80. Dividing both sides by 20, x will be equal to 40, rather x will be equal to 4. So profit maximizing level of output initially will be equal to 4. So let us and since this is our demand function or average revenue function, we also need to find out the marginal revenue function. Here you can see, if I plot this marginal revenue function, we have the same price intercept, which is 90, but the slope is twice that of the average revenue function. Here we have the slope negative 10, here we have slope negative 20. So we will have the same intercept, but this will be our marginal revenue function, which has twice the slope of the demand function. Now we know that at equilibrium, marginal revenue should be equal to the marginal cost, this condition. So this marginal revenue, marginal cost. Okay, at equilibrium what happens? Our quantity is 4, and correspondingly we can find out the price. So price will be here. Okay, so when x is equal to 4, what will be the price will be equal to 90 minus 10 into 4. So price will be equal to 90 minus 40, which is 50. So price came out to be 50. So here we have 50, let us suppose. Now we are being told that government imposes a per unit tax of 20. Okay, and what will be the impact? How will our what will be our new price and output. Okay, so what happens, our marginal cost when a per unit tax is imposed on the monopolist, his cost of production will increase. That means marginal cost will increase. So new marginal cost, let us denote it by MC prime, will be equal to the old marginal cost plus the tax, which is 20. So our new marginal cost will be equal to, so initially the marginal cost was 10 and here we have 20 new. Okay, so that is the tax. So our new marginal cost will be equal to 30. Now what will we do? So let us suppose this is our initial, it was here 10, now it comes out to be, it increases to 30. So this is our MC prime. Again we equate marginal revenue with the new marginal cost, which is MC prime. So marginal revenue, as we know, as we have calculated, it is 90 minus 20x should be equal to new marginal cost, which is this time 30. Solving again, so 20x is equal to 90 minus 30 is 60, dividing both sides by 20, so x will be equal to 30. X will be equal to 3. So this is our new output. So what has happened when we equate the marginal revenue with new marginal cost, so our output has decreased from 4 to 3. By obvious reason, marginal cost of production has increased. Now what will be the corresponding price? To find out the corresponding price, so plug x is equal to 3 into the demand function, so price will be equal to 90 minus 10 times 3, so price will be equal to so price will be equal to 60. So eventually what has happened, monopolist will produce less output at higher prices when a per unit tax is imposed on the monopolist. Okay, we can also find out the profit for the monopolist. So we know that profit is simply equal to the total revenue minus the total cost. Okay, so before the imposition of per unit tax, so profit will be equal to total revenue is price into output minus total cost is 10 into x. Okay, so price initially was 50, so we have 50, and quantity was 40 minus we have 10 times the initial quantity was before the imposition of tax was 40, rather 4, so it is 5 4s are 20, then we have 2 zeros minus 10 4s are 40, so it will come out to be 1960. This will be the initial profit. Now rather initial profit. Now new profit will be equal to, let us suppose this is x star and this is p star, that will be equal to p star into x star minus what will be the new cost, that will be equal to 10x plus per unit tax is 20x, so we have 20x, which is 20x plus 10x is 30x. Okay, so price is 60, quantity is 3, so we have 60 into 3. I have done a big mistake here, so we have 50 into 4 here, which is 200, so we get here 200 minus 40, which is equal to 160. Okay, so here we get 30 into 3, which is new, so 6 3s are 180 minus 3 into 30 is 90, so new profit will be equal to 90. Okay, and initial profit was 160. I hope I have done justification with the calculations. Okay, if you like these videos, please share with your friends. That is the only motivation for me to make more useful stuff for you. Okay, I don't charge any penny or even a single buck for these videos. Okay, we will solve an interesting question on profit maximization in case of monopoly. The question is, a monopolist has constant marginal cost of $1 per unit and zero fixed costs. It faces the demand curve, that is, demand is a function of price, which is equal to 100 upon P, where P is less or equal to 25, or demand will be equal to 0 if price is greater than 25. So I have written here 0, so it is actually 25. What is the profit maximizing choice of output for the monopolist? We need to find out. So we have here, we have demand. If I write the demand function, so Q, quantity demanded, is equal to 100 upon P. Okay, we are being given that this monopolist faces a constant marginal cost of $1 per unit, and we have zero fixed cost. And what will be the profit maximizing choice of output for this monopolist? Okay, so here you can see, if I transpose this P here, so we have P into Q is equal to 100. So what is P into Q? It is actually the total revenue. That is, total revenue of the monopolist is 100. It does not change at all. It is constant here. Okay. What about the total cost of the firm? Monopolist. Since marginal cost is equal to 1 and we have zero fixed cost, total cost will be equal to the integral of the marginal cost with respect to output. So total cost will be equal to 1 dq, and total cost will be equal to Q here. Since we have zero fixed cost, so we don't add the constant of integration here. Simple thing, if marginal cost is constant, total cost will be equal to Q in this case. Having said that, we know that profit of a monopolist will be equal to the total revenue minus the total cost. Now profit will be equal to, what is total revenue? Total revenue is constant, which is 100 here, minus the total cost is Q. Since this is the profit function and we have the constant what we call total revenue here, so this profit will be maximum in this case, since we have only one variable here, which is quantity. So profit will be maximum when this quantity will be minimum. Okay, so when we have the minimum quantity, profit will be maximum for this monopolist. Okay, and since we know that Q is equal to 100 upon P, okay, we know this relation that is being given us the demand function. So since Q should be minimum to maximize profit, in this case this Q will be minimum when price will be maximum. Okay, there is inverse relationship here. So here Q will be minimum when price will be maximum. So what is the maximum price that this monopolist can charge? It's being given us here. P is less or equal to 25. So maximum price will be equal to 25. So quantity will be minimum when we have the highest price, in this case, which is 25, which will give us 4 is the quantity maximizing, rather profit maximizing quantity. So Q should be equal to 4. So here we cannot equate the marginal revenue with marginal cost like we used in our questions related to the profit maximization. If we do here, so total revenue is this, so marginal revenue, we equate marginal revenue with the marginal cost. So since total revenue is P into Q, which is equal to 100, in this case marginal revenue will be 0, and it is not equal to the marginal cost, which is 1. So we cannot use the marginal revenue is equal to marginal cost thing here. Okay, why this is interesting or somewhat different? It is actually the, if I write quantity on the horizontal axis, price on the vertical axis, we have actually a rectangular hyperbolic demand function. So for rectangular hyperbolic demand function, we have constant unit elasticity at each point. Okay, so elasticity of demand is constant. That means total revenue will be the constant in case of curvilinear demand function or rectangular hyperbolic demand function. Okay, so calculate price elasticity of demand for the demand function Q is equal to 1 upon P plus 1 whole square. Q is the quantity demanded, P is the price when price is equal to 2. Okay, so we have the elasticity of demand formula, that is elasticity of demand is being given by, that is equal to the change in the quantity demanded of good Q due to the change in the price of good Q into price divided by quantity demanded of good Q, which is Q at that very price. So first we need to find out this, what we call this derivative. So dq upon dq upon dp will be equal to, so if I rewrite the demand function, it will become p plus 1 raised power minus 2. If I transpose it to the numerator, exponent sign will change. Now its derivative with respect to p, exponent becomes coefficient, so we have negative 2 times p plus 1, and exponent is subtracted by 1, so we have minus 2 minus 1 times the derivative of p, which is 1. Okay, using chain rule here, so we get minus 2 times p plus 1 raised power minus 3. Okay, so dq upon dp is this, so elasticity of demand will be equal to dq upon dp is this term, so if I write it like this, minus 2 divided by, transpose it again to the numerator, so we get p plus 1 raised power 3 times, we have p here and p is being given as 2, so let us first write p, then we have q, q is being given as is 1 divided by p plus 1 whole cube, so it will become negative 2 divided by p plus 1 whole cube times p divided by 1, transpose it here, it becomes p plus 1 whole cube divided by 1. Okay, so here this term and this term gets cancelled, so we have elasticity of demand comes out to be negative 2 times p, which is equal to negative 2 times p is being given as okay, so did I solved it correctly or not? So we have here square, rather we have here square. Okay, so when I transpose it here, so it is square here. Okay, sorry, so 1 p plus 1 will remain here, so we have p plus 1 here, so we get negative 2 times p is 2 divided by p plus 1 means 2 plus 1, so we will get here negative 2 2s are 4 divided by 2 plus 1 is 3. So this is our price elasticity of demand. So our demand function would have been like this, quantity is here, price is here, so we have this kind of demand function, and we were supposed to find out the price elasticity when price is equal to 2, so it came out to be negative 4 upon 3. So in absolute terms it means it is equal to 4 upon 3. It simply tells us if price increases by 1 percentage, quantity demanded will decrease by 4 upon 3 percentage. How to derive the indirect utility function from the given direct utility function? The question is, given utility function, utility is a function of two goods x and y, which is equal to x times y, and the budget constant of the consumer is, that is price of good x times units of good x plus price of good y times units of good y should be equal to the income of the consumer. We need to derive the indirect utility function. Okay, so how do we solve it? So first we want to maximize the given utility function, that is u is equal to x times y, subject to the budget constant, that is price of good x times price of good x times units of good x plus p y times y should be equal to the income of the consumer. Okay, so to find out the indirect utility function, first we need to find out the demand function for good x and y. For that, what we do, we equate the Marner rate of substitution between good x and y, and it should be equal to the ratio of the prices. Okay, price of x upon the price of good y. So we know that it is simply the ratio of marginal utility of good x and marginal utility of good y, and it should be equal to the price of x upon price of y. Okay, so graphically it is simple. We have the given budget constraint. With the given budget constraint, we want to achieve highest possible utility, and it occurs at a point where MRS is equal to the ratio of the prices. Okay, so this ratio is the slope of the budget line, MRS is the slope of the indifference curve. So the tangency between them gives us the demand function for good x and y that we are supposed to find out first. Okay, so MUX is the partial derivative, the change in the utility due to the change in the units of good x consumed, and MUY means the change in the utility due to the change in the units of good y consumed. That is the partial derivatives of the utility function with respect to x and y should be equal to the price ratios. So taking partial with respect to x gives us y first, and similarly taking partial with respect to y gives us x should be equal to price of x upon price of y. Solving for y, we get price of x upon price of y should be equal to, rather it is equal to x. Now we plug this value into the demand function, rather into the budget constant, that means price of x times x plus price of y times the value of y is price of x upon price of y times x should be equal to the income of the consumer. So here we get this cancellation, px into x plus px into x is twice px into x should be equal to m. That gives us x will be equal to m upon 2px. Okay, so this is the demand function for good x. Likewise, we will get the demand function for good y will be equal to m upon 2py. How do we get it? Simply plug x is equal to this stuff into this equation. Okay, so these are the demand functions. To find out the indirect utility function, that is, let's denote by v, that will be a function of price of good x, price of good y, and income of the consumer. So indirect utility function will be derived by plugging the demand function for good x and y into our direct utility function. So we have, in place of x we have m upon 2px, in place of y we have m upon 2py. That means our indirect utility function will be equal to, so we have m square upon 2 into 2 is 4 px times py. That will be our indirect utility function. I hope I make myself clear. Here we will learn about the Harris-Teterow model of migration. So this model was developed by Harris and Teterow in 1970. This model explains the rural-urban migration. So for migration to take place, people compare the actual wage rate in the rural sector with the expected wage rate in the urban sector. And let me explain it with an example. Let us suppose the wage rate in the rural sector is being denoted by WR, that is the actual wage rate in rural sector, and we have the expected wage rate in the urban sector also. Okay, so people compare this actual wage rate in a rural sector with the expected wage rate in urban sector. For the sake of simplicity, let's assume the wage rate in rural sector is, let us suppose it is $40 a day. Okay, and supposedly the wage rate in urban sector is, let us suppose it is $100 a day. Okay, so now we need to find out the expected wage rate of urban sector, and let us denote it by expected wage rate of urban sector will be equal to, it will be equal to the wage rate, the actual wage rate in the urban sector times the probability of getting a job in the urban sector. That means expected wage rate in the urban sector will be equal to the actual wage rate in urban sector. In this example, it is 100 times, let us suppose the probability of getting a job in the urban sector is 50%, a coin toss. Okay, so let us suppose it is 0.5. That means in this case, expected wage rate in the urban sector will be equal to 50. 100 times 0.5 is 50. So people will compare the actual wage rate with the expected wage rate of the urban sector. So here, actual wage rate in the rural sector is $40, So we have $40. This denotes the actual wage rate in rural sector, and we have here 50, which denotes the expected wage rate in the urban sector. Okay, so here you can see the expected wage in urban sector is greater than the actual wage in rural sector. When the expected wage rate in urban sector is greater than the the actual wage rate in rural sector, people will migrate from rural sector to urban sector. Okay, let us explain it diagrammatically. Okay, so let me draw a simple what I call a diagram, and let us suppose we have here O1, or we have here A and B. So we have A, B. Okay, let us suppose this vertical axis on this side shows us the rural sector, and this side shows us the wage rate in the urban sector. Okay, so what we do here, we draw a demand curve for rural sector, and let us suppose it is A prime, that is the agriculture labor supply curve or labor demand curve in the agriculture sector. Likewise, we draw another wage rate, let us say it is our M prime. This is the labor demand curve in the manufacturing sector here. Okay, that is the urban sector in this case. Okay, so what happens at equilibrium? Let me rub this out. So at equilibrium, what will happen? The condition is at equilibrium, actual wage rate in rural sector should be equal to the expected expected wage rate in urban sector. Okay, so here we have two curves. This is the labor demand curve for the rural sector or the agricultural sector, and we have M prime, the labor demand curve for manufacturing sector. So initially these two meet at this point. Let us suppose at this point we have WR. So we have AWR, which is the wage rate in the rural sector, and corresponding to this, let us suppose we have WU, that is the wage rate in the urban. So BWU denotes the wage rate in the urban sector. So is this an equilibrium point? So let me suppose it is at this point where we have L0. That means this portion is in the rural sector and this portion is in the urban sector initially. But in case of this model, this E is not our plausible equilibrium point. Why? We assume that the actual wage rate in the rural sector is less than that of the actual wage rate in the urban sector. That is, wage rate in the rural sector are less than the wage rate in the urban sector, simply because the wage rate in the rural sector are generally they are flexible, seasonal. There is fluctuations in those wage rates, and they are less than that of the urban sector, where we have the organized sector, or where we have some sort of fixed wage rates. Okay, so this is not our plausible equilibrium. Then what is the equilibrium condition? That is, actual wage rate in the rural sector should be equal to the expected wage rate in the urban sector. That is, if I write it again, that is let us denote it by W subscript, or that is, actual wage rate in the rural sector should be equal to the expected wage rate in the urban sector. Okay, now what is WR? So WR will be equal to, now what is expected wage rate in urban sector? It will be equal to, let me write it here, PA upon PB times the wage rate, actual wage rate in urban sector. Okay, and this condition must hold. Now what is PA upon PB? It is, let us suppose PA is the number of jobs available in the urban sector. Okay, so PA denotes the number of jobs. Okay, and PB denotes the number of job seekers who want the employment in the urban sector. So number of job seekers. Okay, so if any person from rural area wants to go to the urban area, he will first find out what is my odds to get the job in the urban sector. That will be equal to the number of jobs in the urban sector divided by the number of job seekers. Okay, let us suppose in this example, let us say we have 100 jobs for the sake of simplicity, and job seekers is 200. Also assume in this example, let us say the wage rate in the what we call the actual wage rate in the urban sector is equal to, let's take a value, let us suppose $100 a day, and let us suppose the wage rate, actual wage rate in the rural sector is $50. Okay, so let us suppose we have 50 here, so $50 is the wage rate in the rural sector. Okay, so let us suppose we have this point here, L1, and we have also the wage rate in the urban sector, which is $100. Let us suppose it is this point, at this point. Okay, so let us denote it by L2, and here we have 100. So here A, and let us give another name to this. So let us say here it is C and D. So AD is the, and this point shows us the equilibrium. Let us show it by E1, and this also shows us another equilibrium point, E2. So we will get this kind of curve here. Okay, so it is not graphically I have not drawn it correctly, so let me try to regraph it. So let us suppose it is here. Okay, so it should be like this. So here we have 50. So if I join this point and this point, okay, this is our another curve. So E1 and E2 joins the two equilibrium pointers. So at this point what happens, the actual wage in the rural sector is equal to the expected wage in the urban sector. Okay, so let me repeat it here. At equilibrium what happens, the actual wage in the rural sector should be equal to the expected wage rate in the urban sector. So in this example we assume there the actual wage rate in the rural sector is $50 and actual wage rate in the urban sector is $100. Okay, PA upon PB shows us the probability of getting a job in the urban sector. Let us suppose we have 100 jobs and there are 200 job seekers. By job seekers we mean those people who want employment in the urban area. Now if this E1 is a point and E2, these are at equality holds at this point. So what happens, AL1 here, AL1 means these people are in the rural sector, and BL2 number of people are in the urban sector. Okay, now what about L1 and L2? What is this distance? So who are these people? That is from L1 to L2. Who are these people in this case? So these are the workers who cannot go to the rural sector but don't want to remain unemployed in the urban sector also. Okay, so then what we need to do? We need to decompose the urban sector into the formal sector and informal sector. Okay, so let me write it here. So we decompose, or we write urban sector. Urban sector is composed of formal sector and informal sector, or unorganized sector. Okay, so this BL2 shows us the amount of number of people who work in the formal sector where they get high wage rate, okay, and get high salary. Now this L1 and L2, these are those very persons who are, so let me write here, L1, L2 are those people who are in the informal sector, workers who cannot go to the rural sector again, but don't want to remain in the remain unemployed in the urban sectors. Okay, so they are the people that are being given the lower wages, and there is high exploitation of those workers. In the formal sector we have B, L2. Okay, this is, so the main essence of the Harris-Tedero model is that people compare the actual wage rate in the rural sector with the expected wage rate in the urban sector. I hope I make myself clear in this video. If you find out these videos helpful, please share this channel with your friends. That's the only motivation for me to make more useful videos for you. Okay, so this was just I didn't touch the assumptions here. It was only to explain how Harris-Tedero model works. We will learn about the physical quality of life index, what we call PQLI. So this index was developed in 1979 by the economist David Morris under the Overseas Development Council (ODC). It was created as an alternative to the pure economic measures like we have the GDP per capita, which fail to compare the real human welfare. The purpose of this is to assess the living conditions in developing countries. Okay, so later developments in this were the PQLI was largely replaced by the Human Development Index, what we call HDI, in 1990s. Okay, so later it was developed, it is further replaced by HDI, which expanded the framework to include economic factors also. Now the definition of the PQLI, what we call the physical quality of life index, it is a composite index that measures the quality of life based on three fundamental, physical and social indicators. So for this we have three indicators, what we call the life expectancy first, life expectancy at birth. Okay, this is one of the indicator. Second is the infant mortality rate. And next we have the basic literacy rate. That is basic literacy rate. Okay, so unlike GDP based measures, the PQLI focuses on health and education outcomes, making it useful for comparing well-being across nations, especially in the low-income countries. Now these core indicators, that is the life expectancy at birth, infant mortality rate, and basic literacy rate. So what are their measurements? So this life expectancy at birth, it is measured as average years a newborn is expected to live. Okay, so it is measured by average years a newborn is expected to live. Okay, so what does it reflect? It reflects healthcare, nutrition, and sanitation. The first, life expectancy at birth. Second, we have the infant mortality rate. Okay, so how do we measure it? It shows us deaths per 1,000 live births before age 1. So it shows us deaths per 1,000 live births before age 1. Okay, before age 1, and we will also with an example learn how to calculate it. So what does this reflect? It reflects, or it indicates, the maternal health and medical access. Okay, this IMR. Lastly, we have the basic literacy rate. So it is measured by the percentage of population aged 15 plus who can read and write. Okay, so it shows us the percentage of population aged 15 plus, who can read and write, who can read and write. Okay, so what does it reflect? It measures the education, access, and human capital. Now, how is this PQLI calculated? So PQLI is calculated by, that is, we take the life expectancy index or life expectancy index. To this we add the infant mortality index, and we add the literacy index, and we divide it by 3. Okay, now each component is converted into a score from 0 to 100. Okay, so this is converted from 0 to 100. This infant mortality, it is also from 0 to 100, this index, and this basic literacy is also, you know, constructed as an index from 0 to 100. Now 0 denotes, in each case 0 denotes the worst observed global performance, so it shows us the worst observed, you know, global performance, and 100 denotes the best observed global performance. Now let us explain it with an example. Let us say if we have in a country where life expectancy index is equal to 70 and infant mortality index is equal to 80 and literacy index is equal to 90, then PQLI, that is physical quality of life index, will be equal to, you know, life expectancy at index, which is 70, plus infant mortality, which is 80, and we have the literacy index, which is 90, and we divided by 3. So PQLI will be equal to, so it comes out to be, now it is 17 24 upon 3. So we get here 3 ones are 3 8s are, so we get 80 as the physical quality life index of this economy, hypothetically. Follow a profit maximization question. The question is given the profit function is, profit is a function of quantity which is equal to 1 upon 2 q square minus 90q plus 300. Find the level of q, that is output, where the profit is maximum. Okay, so given the profit function as pi is a function of quantity which is equal to 1 upon 2 q square minus 90q plus 300. Okay, this is our profit function. Now pi is maximum, so pi is, that is profit is maximum when marginal profit, that is when our marginal profit is equal to 0. Okay, so that means to find out the marginal profit, we differentiate the profit function with respect to output and set it equal to 0. So if we have this profit function, let us say we have quantity on the horizontal axis, profit on the vertical axis. Okay, so we have this kind of profit function. Okay, so this is our profit function. So our profit will be maximum where the slope of the profit function is equal to 0. So taking derivative of this function with respect to q, we get, so derivative of q square is 2q, so we get 1 upon 2 times 2q minus derivative of q in the second term is 1, so we are left with 90, and derivative of a constant is 0, and we set it equal to 0. So this gets cancelled, so we get q is equal to, rather we get q minus 90 is equal to 0. That gives us q will be equal to 90. That means the profit will be maximized when we have the output level of 90. How to find out the minimum point of a function? The question is that y is equal to 3x square minus 6x plus 10. Which value of y minimizes this function? Options are 1, 2, 3 and 0. Okay, so we have y is equal to 3x square minus 6x plus 10. Okay, this is our function. And if I draw a rough graph here, so we have x on the horizontal axis, y on the vertical axis. Okay, so its intercept is 10, so we can draw it like this. It will be like this. So this is our y function. Okay, so now this function will be minimum. Okay, so the minimum point will be at that very point where the slope is equal to 0. Okay, so slope means the derivative of y with respect to x, and we set it equal to 0. Okay, so differentiating with respect to x, derivative of x square is 2x, so we get 2 into 3 is 6, so we have 6x minus derivative of x is 1, so we are left with 6 only, and derivative of a constant is 0, and we set it equal to 0. That gives us 6x is equal to 6, dividing both sides by 6, so we get here x will be equal to 1. Okay, so the minimum point of this function will be when x is equal to 1, y will be minimum. The question is, given the utility function is, utility is a function of two goods x and y which are related like this. U is equal to 4x cube plus 2x square. Find the marginal utility of good x and marginal utility of good y when x is equal to 1 and y is equal to 2. Okay, so given the utility function u is equal to 4x cube plus 2y square, this is our utility function. So first we need to find out the MUX. So marginal utility of good x is simply the change in the total utility due to the change in the consumption of good x, that is the partial derivative. Let's write here partial derivatives of this utility function with respect to x. Derivative of x cube is 3x square, so we get 3 into 4 is 12x. Okay, so we have 3 into x into square, so exponent is subtracted by 1. So this is our marginal utility of good x. Likewise, marginal utility of good y is the change in the utility due to the change in the consumption of good y. That is the derivative of this function partially with respect to y. So derivative, so the derivative of this very term will be 0 because we are taking the partials. Okay, it is treated as constant. Derivative of y square is 2y, so 2 into 2 is 4y. Okay, now we need to find out the marginal utility of good x when x is equal to 1. So plug x is equal to 1 in this equation, so we have 12 into 1 square which is equal to 12. Likewise, marginal utility of good y when y is equal to 2 will be equal to, plug y is equal to 2 in this equation, so we get 4 times 2 which is equal to 8. Okay, these are the marginal utilities when x is equal to 1. Question is, if in an economy marginal propensity to save is equal to 0.2, then the value of investment multiplier is, options are given, we need to find out the correct option. Okay, so investment multiplier is simply equal to, if I write it with k as the symbol, it is equal to 1 divided by 1 minus the marginal propensity to consume, which is equal to 1 divided by 1 minus MPC is equal to MPS. Okay, because we know that the sum of marginal propensity to consume and marginal propensity to save is equal to 1. So we are being given the marginal propensity to save is equal to 0.2. So investment multiplier will be equal to 1 divided by 0.2, which can be written as 1 divided by 2 upon 10, which will be equal to 10 upon 2, which is equal to 5. So the correct option should be 5 here. We will learn how to derive the Marshallian demand function and Hicksian demand function, and how to derive the indirect utility functions and the expenditure functions. Okay, so I will be explaining all the stuff here, so bear with this video. So in the Marshallian demand function, what happens if I take a utility function? Consumer wants to maximize his utility, that is u is equal to x times y. That means consumer wants to maximize his utility subject to the budget constraint. Let us say we have price of x times units of good x plus price of y times units of good y should be equal to the income of the consumer. Okay, so with the given level of income, consumer wants to achieve highest satisfaction, and when we solve it, we get the Marshallian demand function. And what about the Hicksian demand function? In this case, the consumer wants to minimize the cost or expenditure. So consumer wants to minimize the expenditure. Let us say E. What will be the expenditure? That will be price of good x times units of good x plus price of y times units of good y. So with the given prices, consumer wants to minimize his expenditure such that he wants to achieve a certain level of utility. And let us suppose we have the utility function x times y is equal to u. Okay, let's say u naught. With so here what happens, consumer wants to reach a certain level of utility, and to get the certain level of utility he wants to minimize the expenditure. So this is consumer duality problem. Either consumer wants to maximize utility or minimize expenditure. In this case, what happens, with the given level of income, consumer wants to get the highest possible utility or satisfaction. So if I draw a simple graph to make sense here, so let me draw a simple graph to explain the two things. So let us say we have x on the horizontal axis and good y on the vertical axis. So what happens here, consumer is faced with a certain budget. Okay, let us say this is the budget line of the consumer. With this budget line, what does the consumer try to do? He wants to get the highest possible utility. That is, let us say this is indifference curve 1, then we have indifference curve 2. Okay, so with the given budget, consumer wants to reach the highest possible indifference curve to maximize the satisfaction. Okay, and what happens in case of the Hickshian demand or expenditure minimization problem? What happens? So we are saying we have the same two goods x and y. Okay, in this case, utility is held constant in the Marshallian demand function, or in case of maximization problem, consumer's income is held constant. So utility is held constant. That means we have this indifference curve. Okay, so we have this indifference curve, or we have u naught here. Utility is fixed. So with the given, so the consumer wants to reach a certain level of utility, and to get this level of utility, he wants to minimize the expenditure. So let us say this is the one expenditure function, then we have another expenditure function. Okay, so what happens here, we are being given the fixed level of utility. Consumer wants to minimize the expenditure. In this case, we are given the budget line and consumer wants to get highest utility. Okay, so how do we solve them? So there are two methods. Either we use the tangency condition or Lagrangian method. Okay, for the sake of simplicity, let's take the tangency condition. So what will be the optimal condition in the case of utility maximization problem? That will be consumer gets the utility maximization when he equates the marginal rate of substitution between two goods and set it equal to the budget, that is the ratio of the price of x upon price of y. Here also same thing happens, marginal rate of, because what is the optimal point or utility maximizing, rather the optimal point in both the cases when the slope of the indifference curve and the slope of the budget line are equal, and in this case also when the slope of the utility function or the fixed level of utility, this indifference curve, and the slope of this expenditure, price of x upon price of y, they are equal, we get the optimal bundle of good x and y. So here we have also price of x upon price of y. This condition should be held in both the cases. So MRS is nothing, it is the slope of the, this is slope of indifference curve, and px upon py is slope of budget line. Okay, now we know how to calculate the marginal rate of substitution. What is MRS? So let me write it here, then I will wrap. MRS is simply the ratio of the marginal utility of good x upon marginal utility of good y. So MUX is simply the change in the utility due to the consumption of good x. MUY is the change in the utility due to the consumption of good y. That is the partial derivative of utility function with respect to good x, and marginal utility of good y means the partial derivative of utility function with respect to good y. Okay, so if I take the partial with respect to good x, I will get y in the numerator. If I take the partial derivative with respect to y will get the derivative of y will be 1, so we are left with x. Okay, so MRS in the both cases we have y upon x, and here we have also y upon x. Or let me write for both the cases what happens, what we do. In the both cases what we do, we equate for both cases M or S, or whether we have the utility maximization or cost minimization. We equate the marginal rate of substitution between good x and y with price of x, the ratio of the prices of good x and y. Okay, in both the cases we get y upon x is equal to price of x upon price of y. Okay, or y will be equal to y is equal to price of x upon price of y. So let me be price of y times x. Okay, for both the conditions we get this result when we equate MRS with the ratio of the prices. So I don't need to write it here, and also I don't need to write here. Okay, so let me rub because I have to consider other things also. So let me rather repeat it here. So consumer faces a dual choice. Either he wants to maximize utility subject to the given level of income, or he wants to minimize the cost subject to the given level of utility. Okay, so in this case the consumer's endeavor will to maximize the utility, which is equal to x times y, subject to price of x times units of good x plus price of good y times units of good y should be equal to income. In this case he wants to minimize the expenditure, so expenditure will be equal to the prices of good x times their costs correspondingly, and in this case he wants to reach a fixed level of utility, that is x times y should be equal to u naught. In both the cases what happens, with a given budget consumer wants to reach highest possible satisfaction. So budget line is given, we reach highest indifference curve. In this case indifference curve is given and we want to reach the lowest possible ISO cost line. Okay, for both the cases we will get the optimality condition requires we equate marginal rate of substitution between two goods with the ratio of the prices. MRS is simply the ratio of the marginality of good x and y, and px upon py, rather here we have y. This denotes the slope of the budget line. In this case we call the expenditure line, in this case we call it budget line. Okay, so now to find out the Marshallian demand function, what we do, we also call this uncompensated demand function. Okay, so what we do, we plug the value of y is equal to px upon py into x into the budget line. Okay, we plug the value of y here. So when we plug here, what will we get? We get price of x times units of good x plus price of y times units of good y. Here we have price of x upon price of y times x, and it should be equal to the income of the consumer. Doing some basic cancellation, so this py gets cancelled. So we have price of x times x, price of x times x. So we have the same terms, we can add them. So we have twice px into x is equal to m, or x will be equal to m upon 2px. Okay, this is the Marshallian demand function for good x. Marshallian demand is a function of income and prices. Okay, so that means demand for good x is a function of income and price. Okay, now what will we do? We plug x is equal to this stuff into this function. So we will get x is equal to, rather y will be equal to, that means Marshallian demand function for good y will be equal to m upon 2py. Okay, so you can calculate it by yourself also. Plug this value in this equation, you get this demand function. Okay, this was about the Marshallian demand. Now how to find out the Hicksian demand function? So same thing, what we do, we plug the value of y this time in this function. Okay, the constraint function. So we have x times the value of y is price of x upon price of y times x should be equal to the u naught as fixed level of utility that consumer is trying to get. So we have x times x is x square, okay, is equal to, plug this here, so we get u naught price of y upon price of x, or x will be equal to under root of u naught price of x upon, rather we have price of y upon price of x. So this is our Hickshian demand function. These are the Marshallian demand functions. Okay, so this is the Hickshian demand function. So it is a function of utility and prices. Okay, we call it the compensated demand function. Likewise, if we want to find out the Hickshian demand function for good y, we plug this value into this function. Okay, and let me show it here. Okay, don't get confused. So y subscript h means Hickshian demand function will be equal to, so we have price of x upon price of y times the value of x is this. Okay, can I write it like this? U naught raised power 1 upon 2 price of y raised power 1 upon 2 price of x raised power 1 upon 2. To solve this, x, I have just expanded it, so yh will be equal to, so what will we do? Plug this x here, or transpose these here, so we get price of y. If I transpose it here, raised power 1 upon 2 minus, or can we do one thing here? So we get price of y, so here we have x upon y. If I do one thing, let us plug this x here to the numerator. Okay, so we get price of x times price of x raised power minus 1 upon 2, and similarly plug, we have price of y, transpose it here, so exponent sign will change, it becomes negative 1 upon 2, and we have u naught 1 upon 2. So 1 minus 1 upon 2, we will get here price of x raised power 1 upon 2 divided by price of y raised power 1 upon 2. Because bases are same, we can subtract the exponent. Then we have u raised power 1 upon 2. That is, so if I write it in this fashion, so we will get u naught price of x upon price of y. Okay, so this is the Hickshian demand function for, so this is y subscript h. This is the Hickshian demand function for good y here. Okay. Having said that, when we maximize the utility with the given budget line, we got the Marshallian demand functions. When we minimize the utility, expenditure subject to this given level of utility, we got the Hickshian demand function. Marshallian demand function is a function of income and price. Here you can see Hickshian demand is a function of utility and the prices. Now we can also find out the indirect utility functions in case of Marshallian demand function. What we do? So indirect utility function, how do we find out? We plug these values of the demand functions into the utility function here. That is, we will get the utility function, which will be a function of price of good x, price of good y, and income, and I can show it here. So it will be equal to, so xm is, in place of x we write this stuff, in place of y we write this stuff. So we will get m upon 2px times m upon 2py. So we will get m square divided by 4 px py. This is our indirect utility function. Okay. In the same way, what we do, we need to find out the expenditure function in case of Hickshian demand. What will we do? So to find out the expenditure function, we plug the value of x and y into the expenditure function. So what will be the expenditure function? So expenditure will be a function of price of good x, price of good y, holding utility constant, that is the function of utility. So we plug these values, or okay, so let me see if I have the space here. So we have this function, that is u naught, rather we have price of x, so we have price of x times x is under root u naught price of y upon price of x. Plus then we have price of y times y. So the value of y is this, again u naught. So let me rub this out. Okay, so we have u naught price of x, price of y. Solving it, we will get, so doing some simplification, so this under root will go here, so it will become price of x raised power 1 upon 2 u naught 1 upon 2 price of y 1 upon 2, plus here we will also get price of y 1 upon 2 u naught 1 upon 2 price of x 1 upon 2. Okay, so what we have done, we have transposed this here, so we will get here under root of price of x, price of y, u naught, plus here we also got under root of price of x, price of y, and u naught. That means our expenditure function, expenditure will be a function of price of good x, price of good y, and utility, which will be equal to, so we have same terms, it becomes 2 times price of x times price of good y times utility. This will be our expenditure function. Okay, so this is how do we solve how to get the Marshallian demand function, Hicksian demand function, indirect utility function, and expenditure function. I hope I make myself clear and you find out these videos helpful. Please subscribe this channel, share it with your friends. That is the only motivation for me to make more useful stuff for you people. Okay, to find out the demand functions for good x and y from the given utility function and the budget constraint. The question is, given utility function of a consumer is, utility is a function of two goods which is equal to x times y, and the budget constraint that the consumer is facing, that is price of good x times units of good x plus price of good y times units of good y, and it should be equal to the income of the consumer. Okay, we want to find out the utility maximizing bundle, that is we want to find out the demand function for good x and y. Okay, so since we want to utility maximizing bundle, so this question is actually the utility maximization problem. That means consumer wants to maximize the utility derived from the consumption of two goods which are related like this, x times y. Okay, subject to the budget constraint that he is facing, that is price of good x times units of good x plus price of good y times units of good y, and it should be equal to the income of the consumer. So graphically what happens, so if we have good x on the horizontal axis, good y on the vertical axis, we are being given the budget line. Okay, this is our budget line. So this is our budget line. With the given budget, consumer wants to get highest utility. So let's say this is the indifference curve 1, then we have indifference curve 2 here. Okay, so what happens at optimality, what happens, the slope of the budget line and the slope of the indifference curve should be equal. So at equilibrium what happens, slope of indifference curve should be equal to the slope of budget line. What is slope of the indifference curve? It is simply the marginal rate of substitution between two goods. And what is the slope of the budget line? It is the ratio of the prices, price of x upon price of good y. Okay, so this condition should be satisfied. So it happens at this point where the indifference curve and the budget line are tangent to each other. Now MRS is, as we know, it is the ratio of the marginal utility of good x and marginal utility of good y, and it should be equal to the ratio of the prices, that's price of good x upon price of good y. Now what is MUX? It implies marginal utility of good x is simply the change in the utility due to the change in the consumption of good x. MUY is simply the change in the utility due to the consumption of the good, change in the consumption of good y. Should be equal to price of x upon price of y. Okay. Now the partial derivative of this utility function with respect to x means the derivative of x will be 1, so we are left with y. Likewise, the derivative of this utility function with respect to y, so the derivative of y will be 1, so we are left with x, should be equal to price of x upon price of good y. Solving for y, y will be equal to price of x upon price of y times x. To find out the demand function for good x, what will we do? We plug this value of y into the budget line or in the budget constraint. And let me see if I have space available here. Okay, so let me write it here. So plug y is equal to this in this stuff. So we get, let me solve it here. So we have price of x times units of good x plus price of y, and the value of y is, that's price of x upon price of y times x, should be equal to the income of the consumer. Here py gets cancelled, so we have px into x, px into x, so we have the same two terms, we can add them, so that means twice px into x is equal to m, which implies x will be equal to, or x is equal to, it will be equal to m divided by, transpose it here, it gets divided, so we have 2px. This is the demand function for good x. Likewise, the demand function for good y will be equal to m upon 2py. So these are the basically the Marshallian demand functions. If I write it here, x subscript m, y subscript m, superscript sorry, m, these are the Marshallian demand functions. So Marshallian demands are the functions of income and prices. From the Marshallian demand function, we can also find out the indirect utility function. Okay, so this is the direct utility function. Okay, utility is a function of two goods x and y. By indirect utility function, what we mean, the utility is a function of the prices and the income. Obviously, consumer gets utility by consuming some good x and y, but to consume these goods he has to give some price and he should have some income also. That means indirectly utility is a function of income and prices. So how do we find out the indirect utility function? So indirect utility function, let's denote by v. It will be a function of price of good x, price of good y, and income of the consumer. So we plug the Marshallian demand functions into the direct utility function to get the indirect utility function. So in place of x, we have m upon 2px, m upon 2px. In place of y, we have m upon 2py, and it will be equal to m square divided by 2 into 2 is 4, price of x times price of y. This is our indirect utility function. Okay, so the simple difference between direct and indirect utility function is, so when we say direct utility function, we say utility derived from consumption of two goods x and y. Let us say it is a function x times y. Obviously we get the utility by consuming some goods. In case of indirect utility function, what we say? We say so we call this direct utility function. Direct utility function. Now in case of indirect utility function, we have price of x, price of y, and income. That is, utility is a function of prices of goods and the income. Okay, and in this case we got m square upon 4 px py. So in this case, we say that utility depends upon the prices of goods and the income of the consumer, and it makes sense here. Okay, so utility, so we get utility from consumption of two goods, but to consume these two goods, there will be some price that we have to pay and the income that we should have. Okay, that means utility is indirectly, rather a utility indirectly depends upon the prices and the income of the. We learn about the constant elasticity substitution production function, and it is homogeneity. The question is, given the CS production function is Q is equal to under root K plus under root L whole raised power 2, the degree of homogeneity of this function is, options are 0, 1, 2, and 3. Okay, so we have the constant elasticity substitution function, that is, we have output is a function of capital and labor here. So can I write k raised power 1 upon 2 here, plus here we have L raised power 1 upon 2 whole square. Okay, we need to find out what is the degree of homogeneity of this function. Okay, to test the homogeneity, what we do, we increase, and can we write it here like this? Q is a function of capital and labor. Okay, so since this is our given production function, now to find out whether it is homogeneous or not, so what we do, we increase both the inputs by the same proportion. Let us say we increase capital by lambda k and labor by lambda L. Okay, so in place of k we have lambda k raised power 1 upon 2, plus here in place of L we have lambda L raised power 1 upon 2 whole square. Okay, so what will we get? So we have here lambda raised power 1 upon 2, k raised power 1 upon 2, plus here we have lambda raised power 1 upon 2, L raised power 1 upon 2 whole square. So let's take lambda common. So we have lambda raised power 1 upon 2, we are left with k raised power 1 upon 2 plus L raised power 1 upon 2 whole square. Okay, so let us simplify it further. So can we write lambda raised power 1 upon 2 whole square times k raised power 1 upon 2 plus L raised power 1 upon 2 whole square. Okay, we have expanded it. That means when output is increased by, rather when each input is increased by a factor lambda, so we have lambda k, lambda L. What we got here, so here you can see this gets cancelled, we are left with lambda times, so can I rewrite it like this, under root k plus under root L whole square. So what we got, so we got q times, q is a function of lambda k and lambda L, which came out to be lambda times this equation, rather this expression is our original expression, that is times q raised power kl. Here you can see the exponent of this lambda is 1. We can say that the given production function is homogeneous of degree 1. So we say this CES production function is homogeneous of degree 1. Degree 1, because the exponent of the lambda is equal to 1. I hope we will learn about the maxima and minima of a function. So if we have a function y is equal to f of x, so first step is we set the first derivative equal to 0, that is f prime x is equal to 0. Then we take second derivative and evaluate at the critical point that we find out in the first derivative when we set it equal to 0. If the second derivative comes out to be greater than 0, we get a minimum point. If the second derivative is less than 0, when we evaluate it at the critical points, if it is less than 0, then we get the maximum point. Let us suppose we have this total revenue function and we are supposed to find out find maximum total revenue. Okay, maximum total revenue or maximum total revenue, or rather we need to find out the maximum or find the level of output where total revenue is maximum, and find out the corresponding maximum total revenue. If this is our question, how do we solve it? So first step is we take the first derivative of this function. Okay, so let us say t r prime is the derivative of this function with respect to q, which is the first derivative. So derivative of q is 1, we are left with 400 minus derivative of q square is 2q, so 2 into 4 is, sorry, 2 into 8 is 16q, and we set it equal to 0, so this condition holds here. Now when we set it equal to 0, what will we get? We get 16q is equal to 400, dividing both sides by 16, so we get Q will be equal to 400 upon 16. So we have 400 upon 16. So here we have 8 2s are 16, 8 5s are 40, then we have 0, 2 1s are 2, 25s are. So Q is equal to 25. Okay. So our maximum total revenue is maximum when output level is 25. Now we need to find out the second derivative, whether we got this as maximum or not. So this is the first step. Second step is to find out second derivative, that is TR double prime, that is the second derivative. Since this is the first derivative, we take its derivative again and derivate and differentiate with respect to Q. Derivative of a constant is 0, derivative of Q is 1, so we get here minus 16. Since minus 16 is less than 0, that means we got the condition for maximum here. That means in fact when Q is equal to 25, total revenue is maximum. And what is the corresponding total revenue? So total revenue will be equal to, plug this value of Q is equal to 25 into total revenue function. So we have 400 times 25, the value of Q, minus 8 times 25 square. When we solve, we will get the maximum revenue as 5,000. Okay. So its graph will look like this. We have output here, we have total revenue here. So this is our total revenue function, Now this at the point where the slope of this total revenue function is equal to 0, we get quantity as 25, which maximizes the total revenue. So first derivative shows us the point where slope is equal to 0. Okay, that is this T R prime is equal to 0 at this point. Okay, second derivative shows us that the slope is decreasing, that is T R double prime is less than 0. Okay, when we evaluate it at the critical point of 25. Okay, so this is how do we find out the maximum. We will solve the ISLM model using the matrix inversion method. The question is, let the IS equation be y is equal to 840 minus 333i, where y is the income and I denotes the rate of interest. And we have the LM equation, which is y is equal to 704 plus 800i. Solve for equilibrium level of income and rate of interest by using the matrix inversion method. Okay, so we have the two equations. First is the IS equation. So our IS equation is, that is y is equal to 840 minus 333i. Okay, this is our IS equation. Similarly, so what does the IS equation tell us? It shows us the goods market equilibrium. It shows us different combinations of rate of interest and level of income where goods market is in equilibrium. Likewise, we have the LM equation, that is being given us as y is equal to 704 plus 800i. So LM equation shows us the money market equilibrium. Okay, so it also shows us the rate of interest and level of income, the different combinations where the money market is in equilibrium. So if I draw the IS equation, so it will be, if I show the level of income on the horizontal axis, rate of interest on the vertical axis, so this equation is downward sloping. This is our IS equation. And we have the LM equation like this. We have y and I here. Okay, and our LM equation is upward sloping. So this is our LM equation. This shows us goods market equilibrium, this shows us the money market equilibrium. Okay, so what we are supposed to find out, we need to find out the simultaneous equilibrium, that is when we combine these two graphs. So we have y here, I here. Okay, so we have the downward sloping IS equation and upward sloping LM curve rather. So we need to find out the level of income and rate of interest using matrix inversion method. Okay, so let me rub this now. Now since we have to use the matrix inversion method, what we are supposed to do, we need to write these two equations in matrix form, that is in the form that is AX is equal to B. Okay, and where A is, so our A is the coefficient of y's and i's here, or if I rewrite these equations, so we can write y transpose it here, it becomes plus 3i is equal to 840, and if I solve this, so we will get y minus 800i is equal to 704. Okay, so first we need to find out a is the coefficient matrix, which is the coefficients of y's and i's. So in the first equation, or let us say this is equation first, this is equation second. In the first equation the coefficient of y is 1, in the second equation the coefficient of y is again 1. In the first equation the coefficient of I is 3, 3 and 3, and in the second equation the coefficient of I is negative 800. Okay, so this is our A. What is X? X shows us the solution vector, that is we need to find Y and I, and B is the vector of constant terms, so B will be equal to, so B is equal to, what are the constant terms here? We have 840 and 704. Okay, now since we write them into the matrix form, first thing is we need to find out the determinant of the coefficient matrix. Let's find out the determinant of the coefficient matrix. So how do we find out determinant? We multiply the principal diagonal elements first, that is 1 times my negative 800. From this we subtract the product of these two elements, that is 1 into 3, 3, 3. Solving this, we will get the coefficient equal to negative 1, 1, 3, 3. So this is the determinant of the coefficient matrix. Having said that, after that what we do, we need to find out the adjoint of the coefficient matrix, that is ADJ, adjoint of coefficient matrix, and it is equal to, how do we find out the adjoint in the 2 by 2 matrix? Very simple trick is here. So to find out the adjoint of this matrix, what we do, we interchange the principal diagonal elements. So this negative 800 goes here, so we have negative 800 here, and this one comes here. Okay, so we interchange, or we swap the principal diagonal elements, and we change the sign of non-principal diagonal elements. They remain at their positions, but their signs are reciprocated. Okay, so if it is here plus, it becomes negative. If it here plus, it becomes negative here. Okay, so this is the adjoint. After that, what we need to do, so we got the adjoint, then we need to find out the inverse, that is inverse of this matrix. So the inverse of this matrix is equal to 1 divided by the determinant of the coefficient matrix times the adjoint of the coefficient matrix. Now we have calculated, this comes out to be negative this stuff, so we have 1 divided by negative 1, 1, 3, 3, and our adjoint matrix is this minus 800, negative 3, 3, 3, and negative 1 and 1. Okay, when we solve this, okay, so we will get A inverse will come out to be, so this negative 1, 1, 3, 3, it is divided to each of these terms. So solving this, I don't have the space, it will come out to be 0.7061 here. Here we will get plus 0.2939. Here we will get 0.001, and here we get negative 0.001. So what we are doing here, so we are dividing each element by negative 1133. Okay, here we have 2 negatives, they get cancelled. Here we have 2 negatives, they get cancelled. Here we have again 2, they get cancelled. Here we have only 1. So 1 divided by 1133, it comes out to be negative times 0.001. Okay, I hope I am making myself clear here. Okay, I don't have the space, otherwise I could have done this calculation here. Now the value of x will be equal to, our endeavor is to find out the value of x. So x will be equal to, it is equal to So how do I write it here? So we got the inverse here, A inverse. To find out the value of x, we need another equation, that is x is equal to A inverse times B. So A inverse is this matrix times B, which is the vector of the constant terms. We have written it here. So we need to so x will be equal to, so we know that x is equal to y and I is a solution vector, which will be equal to A inverse, which is 0.7061, then we have 0.001, we have 0.2939, and we have negative 0.001. To this we multiply by the vector of constant terms, which is 840, 704. Okay, so our x will be equal to, now we need to do the matrix multiplication. And how do we write? So we multiply each row with their corresponding column. That means we multiply, we have 0.7061 this, and we multiply row with the column. So we have 0.7061 and we multiply it by 840. Then we add again and we multiply this term with this, so we have 0.2939 and we multiply it with 704. Okay, after that, so we are done with this row and with this column. Then we multiply this row with this column. Okay, so we have 0.001 times 840 plus we have negative 0.001 and we multiply it with 704. Okay, that means our x will be equal to, doing this calculation, when we calculate we will get 799 and here we will get 0.13. And since we know that x is equal to yi, so x is this term, so which is equal to 799 0.13, which gives us the value of y, implies y will be equal to 799, which is our equilibrium level of income, and rate of interest is 0.13. Okay, so graphically how do we explain it? So let me rub this out here. So here we have y and I. Let us suppose this is our I situation, which is downward sloping. Then we have y and I here, and we have the LM equation, which is upward sloping. Then when we combine these two graphs, we will get, we have y here and rate of interest here, downward sloping i's curve and upward sloping LM curve. So they intersect at this point. This gives us, at this point we have y is equal to 799 and rate of interest is 0.1. How to find out the profit maximizing level of output from the total revenue and total cost function? We have the total revenue function is 30q minus q square. Q denotes the output, TR is the total revenue. Cost function for the firm is C is equal to 20 plus 4q. Find profit maximizing level of output. Okay, so we know that profit is equal to total revenue minus the total cost. Okay, let us denote it by TC, that is total cost here. So in this case our profit will be equal to, so total revenue is 30q minus q square. To this we subtract the total cost, so we have minus 20 and minus 4q. So total profit, our profit function will be equal to, so we have 30q minus 4q, which comes out to be, in this case 30q minus 4q is 26q. So we have 26q minus q square minus 20. Okay, for what is the first order condition for profit maximization? So first order condition for profit maximization requires that the marginal profit with respect to output should be equal to 0. That means we take the derivative of this function with respect to output and set it equal to 0. So which implies, which is equal to, so d pi upon dq means the derivative of this function with respect to q. Derivative of a q in the first term is 1, so we are left with 26, minus derivative of q square is 2q, and we set it equal to 0. Okay, and derivative of a constant is 0, we know that thing. And that implies 2q is equal to 26, dividing both sides by 2, q will be equal to 26 upon 2, which is equal to 13. So we get first order condition, we got the critical value, that is output level is 13. This is the first order condition. Now what about second order condition? So we need to check the second order condition also. So for second order condition, we take the second derivative, that is d square pi upon dq square. Okay, so this is the first derivative. Now taking the derivative of first derivative gives us the second derivative. Derivative of a constant is 0, derivative of q is 1, so we are left with minus 2 here. So we got minus 2. Since minus 2 is less than 0, okay, we get the condition for maximum, that is second order condition satisfies the condition for maximum. Okay, so if it is like this, if I show it here, so if this is our profit function, rather this is our profit function, so let us say, so first derivative shows us the slope where shows a point where slope is equal to 0, that is first order condition, and second order condition shows us the slope should be decreasing for maximum. Okay, so if it was greater than 0, then we will get the condition for minimum. Okay, in this case, profits will be maximized when we have the output level of 13. Okay, if we have output on the horizontal axis, profit on the vertical axis. How to find out the value of the labor that maximizes average product of labor given output is a function of labor, so q is equal to L square times e raised power negative 0.01 L. Okay, we need to find out the value of L that maximizes average product of labor. Okay, so first thing is we need to find out the average product of labor, that will be equal to total output divided by labor, so it will be equal to L square e raised power minus 0.01 L, to this we divide by L, so we will get here L, 1 L will get cancelled, we get e raised power negative 0.01 L. Okay, our average product of labor is equal to L times e raised power negative 0.01 L. Okay, so to find out the maximum value of L that maximizes average product of labor, what we do, we take the derivative of average product of labor with respect to L and set it equal to 0. Okay, so first we need to find out the first derivative. Now here we have two functions. Okay, so let us suppose this is we have L and e raised power this, so we have two functions in product form. We need to apply the what we call the product rule of differentiation. Let us suppose it is u and this is v. Now to apply to differentiate it with respect to L, we apply the product rule function, that is the derivative of average product of labor with respect to L will be equal to, so what we do in the product rule, we write the first function, okay, that is u, and take derivative of the second function with respect to L, that is or let us write it here to make things clear. Okay, so let u is equal to L and v is equal to e raised power negative 0.01 L here. Okay, then it means d APL upon DL means we write the first function, okay, and take the derivative of the second function, that is dv upon dl. Then we add and write the first function, rather the second function, and take derivative of first function, that is du upon dl. Okay, so what is u? U is L. dv upon dl means derivative of this function, this exponential function with respect to L. So we write here e raised power minus 0.01 L, and we apply here chain rule and take derivative of the exponent. So the derivative of exponent is minus 0.01. Then we write v is e raised power minus 0.01 L times derivative of the first function, which is L. The derivative of L is 1. Okay, how do we take the derivative of e raised power? We have e raised power minus 0.01 L, so we know that the derivative of e raised power nx is equal to e raised power nx times the derivative of the exponent with respect to x, which is n. Here we have e raised power minus 0.01 L, so its derivative with respect to L was first the given function, that is e raised power minus 0.01 L times the derivative of the exponent, which is minus 0.01. that we have done here. Okay, don't get confused here. And we are supposed to set it equal to 0. Okay, that is the condition. So let's take e raised this term constant, so we are left with e raised power minus 0.01 L, and here we are left with minus 0.01 L plus 1. Okay, and we set it equal to 0. Now we can do one thing here, since it is equal to 0, and we also know that the negative exponential function is never equal to 0. Although this e raised power minus 0.01 L gets closer and closer to 0 as L increases, it never actually equals 0 for finite values of L. That implies, so if I divide both sides by this function, we will get 1 minus 0.01 L is equal to 0, or 0.01 L is equal to 1, or 0.01 can be written as 1 upon 100 L is equal to 1, which implies L will be equal to 100. Okay, so this was the first order condition. Now in the second order condition, what we need to do, we need to take the second derivative, that is the d square APL dl square, okay, and see its value when we evaluate it at L is equal to 100. If it came out to be less than 0, then our L maximizes the average product of labor. Okay, so I don't have the space and time here. You can take the derivative and check it yourself whether it comes out to be second derivative comes out to be less than 0. If it is less than 0, then the condition for maximization is satisfied. Let us solve a utility maximization problem. We have the utility function of the consumer, which is equal to u is equal to xy upon x plus y, where x and y are the two goods the consumer consumes, and he has the budget constraint, that is 10x plus 40y is equal to 180. 10 is the price of good x, 40 is the price of good y, and 180 is the total income of the consumer. Okay, so we know that for utility maximization, we equate the marginal rate of substitution between good x and y with the budget ratio, that is price of x upon price of y. And let us be here specific. So we have price of good x is $10, price of good y is equal to $40, and income of the consumer is equal to 180. Okay, so given this budget, what we want to do, we want to maximize the utility here. So utility maximizing condition is that we equate the marginal rate of substitution, MRS, with the ratio of the prices of the goods. Okay, this is the slope of the indifference curve, and this denotes the slope of the budget line. Okay, so what happens exactly, we have a simple graph. We have x on the horizontal axis, y good on the vertical axis, with the given budget. Let us say this is our budget line. Consumer tries to achieve highest utility, and highest utility will be achieved where the budget line and indifference curves are tangent to each other. Okay, so this is the condition where M or S is equal to the price of x upon price of y. Having said that, now we know that MRS is simply the ratio of the marginal utility of good x and marginal utility of good y, and we equate it with the px upon py. Now MUX is simply the change in the utility due to the change in the units of good x consumed, and marginal utility of good y is the change in the total utility due to the change in the consumption of good y, and it should be equal to the ratio of the prices. That is being given us as 10 upon 40, so which is equal to 1 upon 4. If I write it here 10 upon 40, you know we can divide both numerator and denominator by 10, so we get 1 upon 4. Okay, let me took it like this. Okay, now we need to find out du upon dx. Okay, so du upon dx, this partial derivative du upon dx, so we differentiate this utility function with respect to x. Okay, so we have two functions here in the numerator function and denominator function. We apply here what we call the quotient rule of differentiation. In that, what we do, first we take the denominator function. Okay, so we have x plus y and multiply it with the derivative of the numerator function, that is d upon dx of xy. Then we subtract the numerator function, this which is x times y, and we multiply it with the derivative of the denominator function, that is d upon dx of x plus y, and divided by the square of the denominator function, that is x plus y whole square. Okay, let us solve it. So here we have x plus y first. Now derivative of x is 1, so we are left with y only, minus, then we have x times y, now the derivative of x is 1 here, and derivative of a constant is 0, because we are taking partials with respect to x here. Okay, so we get x times y times 1, okay, times 1, divided by x plus y whole square. So let us further simplify it. So we have xy, so which is xy plus y square minus xy, divided by x plus y whole square. So xy and xy gets cancelled. We get here y square upon x plus y whole square. Okay, now let me make the space. So we got du upon dx came out to be y square upon x plus y whole square. Likewise, when you take du upon dy, that is the partial derivative of this function with respect to y, again we apply the quotient rule and we will get x square upon x plus y whole square. You can check it by yourself also. Now we know this is the utility maximizing condition. Mux is this term, muy is this term, so we have first y square divided by x plus y whole square, divided by, then we have x square divided by x plus, okay, so I am not visible, I guess, let me write it here, x plus y whole square should be equal to ratio of the prices, which is 1 upon 4. So we can write y square divided by x plus y whole square times, transpose it to numerator, it will get reciprocated and multiplied, so we get x plus y whole square divided by x square, and it should be equal to the ratio of the prices. So this term gets cancelled. We are left with y square upon x square is equal to 1 upon 4. So can we rewrite it like this? Y upon x whole square is equal to 1 upon 4, or y upon x is equal to, take this exponent, it becomes under root, so we get 1 upon 4, which is equal to 1 upon 2 here. Okay, because we get it, okay, it becomes under root 4, so here we have under root 4, which is equal to 1 upon 2. So we got y upon x is equal to 1 upon 2, which gives us y will be equal to, rather x will be equal to, implies x is equal to 2 times y. Okay, now we plug this x is equal to 2y into the budget constraint. Here we put the value of x, so we have 10 times 2y plus 40y should be equal to 180. So this is 10 into 2 is 20, 20y plus 40y is 60y, implies 60. Y is equal to 180. Dividing both sides by 60, so we will get y will be equal to 6 3s are. So y will be equal to, y will be equal to 3. That means consumer will consume 3 units of good X. Now what about Y? So we got this condition here. So we have X is equal to 2 times Y. So we have X is equal to 2 times the value of Y is 3 here. So X will be equal to 2 3s are 6. So X is equal to 6. So consumer will consume 6 units of good Y and 3 units of good X. How to solve a national income model using Kramer's rule? The question is, using Kramer's rule to solve the following national income model, we need to find out the equilibrium level of income and the consumption using the Kramer's rule. Okay, so first thing is first, what we need to do, we need to solve this equation. We need to write the endogenous variables on the left side or left hand side and exogenous variables on the right hand side. Okay, so here our endogenous variables are Y, that is income, and consumption. Okay, so solving the first first equation, so can I write it like this? So we have Y, transpose this here, it becomes minus C is equal to I plus G. Okay, so the first equation says us that income is equal to consumption expenditure plus investment expenditure plus government spending. Okay, and consumption is a function of income, where C is equal to A plus BY. A denotes the autonomous consumption when the level of income is 0. B is the marginal propensity to consume, and Y is the income. Okay, so solving first, we got this very thing. We have the endogenous variables Y and C on the left hand side, and constant terms, that is investment and government spending, which are autonomous here on the right hand side. Likewise, what we need to do, we need to write the endogenous variables to the left hand side in the second equation also. So we have by here, transpose it to the left hand side, it becomes negative by. Okay, negative by. Then we have plus C is equal to, here we have A. Okay, next step is to write them into matrix form. Okay, so let me use the proper color here. So let me write it in this fashion. So we have I plus G, and here I write it A. Okay, so what we need to do, we need to write them in the matrix form first. So in the form, that is A X is equal to B. Okay, what is our A? A is the coefficient matrix. Okay, so A is a coefficient matrix, that is we have the coefficients of Y's and C's. In the first equation, the coefficient of Y is 1, so let us write it here 1. In the second equation, coefficient of Y is B, negative B rather. In the second term in the first equation, the coefficient of C is negative 1, and coefficient of C in the second equation is 1. So this is our what we call a coefficient matrix. Next thing is, what is here X? X is the solution vector that we are supposed to find out. X is equal to Y and I. And what about B? B is the vector of constant terms. Okay, so it is a vector of constant terms. So what are our constant terms? In the first equation we have I plus G. In the second equation we have A. Okay, now first thing is, what we need to do, we need to find out the determinant of the coefficient matrix. Okay, so to find out the determinant of the coefficient matrix, what we do, since this is our coefficient matrix, to find out the determinant, we multiply the principal diagonal elements first, that is 1 into 1 is 1. From this we subtract the non-principal diagonal element. So minus B times minus 1 is plus B. Minus into minus is plus, so we get here plus, and since we have first minus, so we get here 1 minus B. Okay, don't get confused. We have 1, so we have 1 into 1, then we subtract, and we have minus B times minus 1. Here you can see, we 1 into 1 is 1, then we have minus B into 1 is plus B, so we get 1 minus B, that I have written here. This is our determinant of the coefficient matrix. Now to find out the value of equilibrium value of Y, what we do, we form a new matrix, let us say A2, which is formed by replacing the first what we call first column of the coefficient matrix with the vector of constant terms. Okay, so we replace 1 and minus b with I plus g and a. So I write here I plus g, then we have a, and other things remain same. We have -1 and we have 1. Okay, now we need to take the determinant of this a2. So determinant of a2, again, how do we find out the determinant? We multiply the principal diagonal elements first. 1 plus g times 1 is 1 plus g times 1 is 1 plus g. 1 plus g, rather it is I plus g here, sorry. Then we subtract and multiply the non-principal diagonal elements. We have a into -1 here. We have a into -1. So it becomes I plus g minus a into -1 is plus a. Okay, so this is our a2. That means the value of y will be equal to find out the equilibrium value of y. What we do to find out the value of this element or this element, what we do, we write the determinant of the new element that we the determinant of the new matrix a2 and divide it with the determinant of the coefficient matrix, which is a. So a2 is our I plus g plus a, and our determinant is 1 minus b, rather it is I here. Okay, so this denotes our equilibrium level of income. Likewise, to find out the equilibrium value of investment, what we we are supposed to find out the value of consumption here. Okay, now to find out the value of c, what we do, we replace the second column of the coefficient matrix with the vector of constant terms. So we form a2 I'm really sorry, we write first a1 here. Okay, so a1, here we have a1, here we have a1. Okay, I don't know what I have, why I am not able to concentrate on this. Okay, so a1 is a matrix which is formed by replacing the first column of the coefficient matrix with the vector of constant terms. Then we need to find out a2, a new matrix which is formed by replacing the second column of the coefficient matrix with the vector of constant terms. So we have I plus g, then we have a, we have replaced it, and 1 and minus b remain the same. Okay, then we need to take the determinant of a2 again. So how do we find? Multiply these two elements. So we have a into 1 is a, then we subtract and multiply these two elements. We have -b times I plus g. Okay, so we get here a2, the determinant of a2 comes out to be a minus into minus is plus, so we get plus b times I plus g. That gives us consumption will be equal to, then the value of c will be equal to the determinant of a2 upon the determinant of the coefficient matrix. Okay, so here c will be equal to determinant of a2 is a plus b times I plus g divided by 1 minus b. We have 1 minus b. Okay, that is how do we solve it using Cramer's method, rather Cramer's rule. And let me repeat it again. Okay, so this is the recapitulation here. So we have two equations, that is y minus c is equal to I plus g, then we have minus b, y plus c is equal to a. Okay, so first thing was we write them into the matrix form, that is a x is equal to b, where a is the coefficient matrix. We have the coefficient of y is 1, coefficient of y in the second term is minus b, then we have the coefficient of c minus 1, and here we have 1. Then x is equal to y and c, that we are supposed to find out, vector of constant term. It should be equal to the vector of constant term, that is I plus g and a. Then what we do, we find out the determinant of a, which we got as 1 minus b. Okay, and next we formed a new matrix a2. So to find out the value of y, what we do, we replace the first column of the coefficient matrix with the vector of constant. That is, we got I plus G A, and we replace it with this, and -1 and 1 remained same. Okay, then we were supposed to find out the determinant of A2. Okay, that we got here somewhere. The determinant came out to be this thing. Okay, then the value of y would have been the determinant of A2 upon the determinant of the coefficient matrix. Likewise, to find out the value of C, to find out the value of C, we form a new matrix, that is A2, which is formed by replacing the second column of the coefficient matrix with the vector of constant term. So we have 1 and minus b remain the same, but in place of -1 and 1 we write I plus G, and then we have A. Then we took the determinant of A2. When we took the determinant of A2, that came out to be, rather this is the determinant of, so sorry, here we have to find out, here it is A1. Again I am doing the same mistake. Here we have A1. Okay, so A1, the determinant of A1 came out to be I plus G plus A. Okay, so I plus G plus A, or let me write it here. So A1 was I plus G plus A divided by 1 minus B. Okay, in this equation A2 is this A plus B times I plus G. That gives us C would have been equal to the determinant of A2 upon A. So A2 is A plus B times 1 I plus G divided by 1 minus B. Okay, this is how do we solve the income model using Kramer's. The question is, derive the marginal revenue function for the demand function Q is equal to 400 minus 0.1 P, where P is the price and Q is the quantity or output. Options are being given. We need to find out the correct option. Okay, so we have the demand function is Q is equal to 400 minus 0.1 P, and we are supposed to find out the marginal revenue. Okay, so to find out the marginal revenue, first we need to find out the total revenue, and we know that total revenue is equal to price into output. Okay, so that means we need to solve this equation for P. Okay, so let us transpose this term here. So it becomes positive 0.1 P is equal to 400, and transpose this Q here, it gets subtracted, it becomes negative Q. So 0.1 can be written as 1 upon 10. P is equal to 400 minus Q. Now transpose this 10, it gets multiplied to each of these terms. That means D will be equal to, rather P will be equal to 400 into 10 is 4000 minus 10 into Q is 10Q. So this is our inverse demand function, but we are supposed to find out the marginal revenue. So first we need to find out the total revenue, which is price into output. So P is this very function, so we have 4000 minus 10Q. To this we multiply by Q. Then our marginal revenue will be equal to the change in the total revenue due to the change in the output. That is the derivative, or let us simplify it further. So we have 4000 times Q is 4000 Q minus 10Q times Q is 10Q square, 10Q square. Okay, so this is our total revenue function. Now the derivative of total revenue function with respect to output gives us the marginal revenue. So the derivative of Q is 1, we are left with 4000 minus derivative of Q square is 2Q, so 2 into 10 is 20Q. That means our marginal revenue function will be 4000 minus 20Q. Okay, so that gives us B option should be correct. Next question is, what is the point elasticity of demand when price is $12 for the demand function P is equal to 60 minus 3Q, where P is the price, Q is the quantity. So we have this demand function P is equal to 60 minus 3 times Q. Okay, so elasticity of demand is being given by, that is the change in the quantity demanded due to the change in the price times price upon quantity demanded at that very price. So we need to find out dq upon dp. Since this function is in terms of Q, we need to solve it for Q here. Okay, so rewriting the demand function, this is the inverse demand function, and let's write it as the ordinary demand function. So we get 3Q is equal to 60 minus P, divide both sides by 3. So Q will be equal to 60 upon 3 is 20 minus 1 upon 3 P. Okay, now we can take this derivative dq upon dp. But we are being told that when price is equal to 12, what will be the quantity demanded? So quantity demanded will be equal to 20 minus 1 upon 3 times 12. So Q will be equal to 20 minus 3 ones are 3 fours are 12, which is equal to 16. Rather, here we get 20, or let's write it here. So we get 20 minus 4, which is 16. Then elasticity of demand is dq upon dp. That means we need to find out this derivative first. The derivative of this function with respect to p. Derivative of a constant is 0, derivative of p is 1, so we are left with minus 1 upon 3. To this we multiply by p, which is being given us as 12, divided by quantity demanded at that very price is 16. So here we get 3 ones are 3 fours are, then we get 4 ones are 4 fours are, so we get negative 1 upon 4, which is equal to 0. Minus 0.25. So elasticity of demand will be equal to 0.25 negative. That means if price increases by 1%, quantity demanded will decrease by 0.25%. Next question is, in a closed economy, if marginal propensity to consume is 0.75, marginal tax rate is 30%, find value of government expenditure multiplier. Options are being given. We need to find out the correct option. Okay, so government expenditure multiplier, let us denote it by K subscript G. It is being given by 1 divided by 1 minus MPC plus MPC times marginal tax rate or marginal rate of taxation. Now in this case we can see, so we have 1 divided by 1 minus MPC is 0.75 and it can be written as 3 upon 4. This can be written as 3 upon 10. So we have 1 minus 3 upon 4 plus then we have 3 upon 4 times 3 upon 10. Okay, so government expenditure multiplier will be equal to 1 divided by, so here it is 1 minus 3 upon 4 is, it becomes 1 upon 4. So we have 1 upon 4 plus 3 3s are 9 plus rather divided by 4 10s are 40. So we will get 1 whole divided by, so let us make denominator same. So we get 9 plus 4 is 13 divided by 40, or we get 40 upon 13. So if we write it like this, so we have 40 here, so 13 3s are 39, then we have point, here we have 1, then 13, okay, so then again we have 13 zeros are 0, so we will get something 3.05 or something. So since we have 3.2 here, so let's take this very value. Next question is, for the production function Q is equal to 20 times K to the power 0.5 times L to the power 0.5, derive capital as a function of labor when the ISO count Q is equal to 100. Options are being given. We need to find out the correct option. Okay, so we have output, that is Q is a function of capital and labor, which is equal to 20 times k to the power 0.5 can be written as k raised power 1 upon 2, and L to the power 0.5 can be written as L raised power 1 upon 2. Okay, we need to find capital as a function of level in this case, and we are being told that our output level is 100. Okay, so plug Q is equal to 100 in this equation, so we have 100 is equal to 20 times k to the power 1 upon 2 times L to the power 1 upon 2. So we can rewrite it like this, 20 k to the power 1 upon 2 L to the power 1 upon 2 is equal to 100. Dividing both sides by 20, we will get k raised power 1 upon 2 L raised power 1 upon 2 is equal to, so we have, if we divide both sides by 20, we will get here 21s are 25s are, so we get here 5. Now we can rewrite it, since we need to solve it for k, so k raised power 1 upon 2 will be equal to 5 divided by, and when I transpose it, it gets divided, so we get L raised power 1 upon 2, which implies k will be equal to, when I transpose exponent, it becomes square here. If it is 1 upon 2, it becomes 2 upon 1. So we get here 5 divided by L raised power 1 upon 2 whole square, because 1 upon 2 will become 2 upon 1. So 2 upon 1 is 2. That means k will be equal to 5 into 5 is 25. Okay. Or let us write it again. I don't have the space, so let me make the space here. So we have k is equal to 5 square divided by L raised power 1 upon 2 square, which is equal to 5 into 5 square is 25 divided by here square, this 2 and 2 gets cancelled, we are left with L. That implies k is equal to 25. Transpose this L to the numerator, it gets multiplied, but exponent sign changes. So the exponent is here 1, it becomes -1. So this is our capital as a function of lever. So the correct option should be 25 L raised power -1. Next question is, find the determinant of the matrix A is equal to 4, 2, 9, 6, 5, 0, 1, 2, 4. Options are being given, we need to find out the correct option. Okay, so determinant of A, that is the determinant of this matrix, is equal to, so we write first element, which is 4, and mentally delete the row and the column in which it appears, and take the determinant of the remaining elements. That means we delete this row and this column and take determinant of the remaining elements. That is 4 times, now what is determinant of this? 4, 2, 0, 4. So we have 5, rather 5, 2, 0, 4, and its determinant is simply, we multiply these two elements, so 5 into 4 is 20 minus 0 into 2 is 0. Okay, then we write the second element with negative sign. Okay, first element is written with positive sign, second element is written with negative sign. In this case, we delete the row and the column in which the second element appears and take the determinant of the remaining element. So this row and this column, when it is left out, so we have 2, 9, 2, 4, and we take its determinant. Okay, so we have 2 4s are 8 minus 9 2s are 18. Okay, then we write the third element with a positive sign. Okay, the signs change from positive to negative, so first is positive, then negative, then positive. So we write positive 1, and we multiply it with, rather we remove the row and the column in which it appears and take determinant of the remaining elements. So remaining elements are 2, 9, 5, 0 this time. Okay, so 2 into 0 is 0 minus 9 5s are 45. Okay, simple thing. So we write the first element and multiply it with this determinant. Then we write second element with negative sign and delete the row and the column in which it appears and take the determinant of the remaining elements, and so on. So we will get here 4 times 20. Then we have minus 6, 8 minus 18 is minus 10. then we have plus 1 times minus 45. So we will get here 2 4s are, which is 80. So here it is plus 60, then we have minus 45. So it will come out to be 140 minus 45, and it comes out to be 10 minus 5 is 5. Then we have 13 minus 4 is 9. So the correct option should be 95. That is, the determinant is 95 in this case. If y is equal to 2x square plus 3x minus 4 whole raised power 99, find the derivative dy upon dx. Okay, so we have the function y is equal to 2x square plus 3x minus 4 whole raised power 99. Okay, now dy by dx will be equal to dy upon dx will be equal to, so here we apply the chain rule. Okay, so first we apply the power function rule. That means 99 becomes coefficient 99 times 2x square plus 3x minus 4, and 99 is subtracted by 1, so we get here 98 times d upon dx of the terms which are in the brackets, which is 2x square plus 3x minus 4. Okay, so dy upon dx will be equal to 99 times 2x square plus 3x minus 4 raised power 98 times the derivative of these terms with respect to x. Okay, so derivative of x square is 2x, so we have 2 into 2 is 4x times we get 4x plus derivative of x is 1, so we are left with 3, and derivative of a constant is 0, so we get 99 times 4x plus 3 times 2x square plus 3x minus 4 raised power 98. Okay, this is how do we apply the chain rule. So first we use the power function rule here, then we multiply it with the derivative which is in the brackets, the terms which are in the brackets. The demand function is, that is PD is equal to 3x square minus 20x plus 5, where x is the output, P is the price, and supply function is PS is equal to 15 plus 9x. We are supposed to find out the producer surplus. Options are being given, we need to find out the correct option. So we have the demand function and supply function. If I draw a simple graph here to make the things clear, so if I draw it like this, we have the quantity on the horizontal axis, which is denoted by x, and price on the vertical axis. We have a non-linear demand function here. Okay, so let us suppose we have this kind of demand function. Okay, this is our PD, and we have the supply function as 15 plus 9x, which is upward sloping supply function. Okay, let us say this is our rather PS, which is the supply function. We are supposed to find out the producer's surplus. Okay, to find out the producer surplus, first what we need to do, we need to find out the equilibrium. So equilibrium occurs where demand is equal to supply, where quantity demanded is equal to supply. That is the point where these two curves meet. Okay, so at equilibrium what will happen, PD will be equal to PS, that is demand is equal to supply, because this is the demand function, this is the supply function. So equating them with each other, we get 3x square minus 20x plus 5, and we equate it with 15 plus 9x. Okay, so solving further, we have 3x square minus 20x, transpose it here, it becomes minus 9x, then we have plus 5, transpose it here, it becomes negative 15, and we set it equal to 0. So here we get 3x square minus 29x, then we have 5 minus 15, which is negative, rather negative 10, and we set it equal to 0. This is a quadratic function, and we will solve it using the use the quadratic formula here. Rather, here we have the coefficient of x square is, let us say it is a, it is 3, coefficient of x is negative 29, which is b, and we have the constant term which is negative 10. Using the quadratic formula, how do we use the quadratic formula? We know it. So x will be equal to, that will be equal to minus b plus minus b square minus 4 times a times c upon 2 times a. Okay, so having said that, let us put the values here. So we have x is equal to, so we have negative b means negative of, let us write it here, negative of minus 29. Then we have plus minus b square means negative 29 whole square. Then we have minus from the formula. Then we have 4 times a times c. So we have 4, the value of a is 3, and the c is here negative 10 upon 2a. 2 times the value of a is 3. So x will be equal to, so negative times negative is positive, we get 29 plus minus, now square of a negative number is always positive, so the square of 29, I calculated it, it came out to be 841, and this is here negative times negative is positive, so 4 3s are 12, 10s are 120, so here we have 120 upon 6. So we will get x will be equal to 29 plus minus sum these two terms, two numbers rather, we get 961 upon 6, and which will be equal to 29. The square of 96, we have 961, its square will be equal to 3 3s are 9, then this gets doubled, so it becomes 6. So here we have 60, so 61 into 1 is 61, that means the square root of 961 is 31. So we get 31 upon 6. Okay, so after that, that gives us two values of x. There is either x is equal to 29 plus 31 upon 6, or x is equal to 29 minus 31 upon 6. Here we will get a negative number. 29 minus 31 is minus 3 upon 6, so quantity cannot be negative, so we can outrightly reject this negative quantity. That means quantity, equilibrium quantity will be equal to 29 plus 31 is 60 upon 6, which comes out to be 10. Okay, so we have found out the equilibrium quantity, which came out to be 10 here. Now we are supposed to find out the equilibrium price. Plug x is equal to 10 either in demand or supply function. Let's put it in the supply function. That will give us the equilibrium price here, that is 15 plus 9 times 10, so which comes out to be, p will be equal to 15 plus 9 tens are 90 plus 15 is 105. Okay, so this is the equilibrium price, this is the equilibrium quantity. Okay, now I need to rub this all stuff to find out the consumer surplus. For that, let me rub this. So what we got after solving this, we got a price came out to be 105 and equilibrium quantity came out to be 10. So here we have 10. Now we are supposed to find out the producer surplus. So producer surplus is simply the difference between the amount a producer receives for a product and the minimum amount they would be willing to accept. Okay, graphically it is simply the area which is above the supply function and below the equilibrium price. So the area of this very region okay, so let me see if I have done it correctly. Okay, that's correct. So the area which is above the supply function or supply curve and below the equilibrium price gives us the producer surplus. Graphically it will be, to find out the area of this very region, what we need to do. So producer surplus, let us denote by PS, is simply equal to, so first we need to find out the area of this rectangular box. So first we find out the area of this rectangular box. Okay, whole area. From this we subtract the area which is below the this very area, this very quadrilateral, that is this, and we will be left with the above triangular shaped curve. Okay, Let us first find out if we can okay, we don't need we can solve it using two methods, either graphically. So we know the intercept of the supply function is 15, and let us see if we can solve it like this. So this is, since this is a what we call a right angle triangle, so it is, so producer surplus will be equal to the area of this very triangle. So we have why price, rather price is 105 here, sorry, 105. So and the difference, and this length is 105 minus 15, so 105 minus 15, which is base, into what is height. Height is from 0 to 10, 10 divided by 2. This is the area of a right angle triangle, that is 1 upon 2 into base into height. Okay, here base is, if we assume this is base and this is height, because we know it is at 10. So let us see if we can find it like this. So 105 minus 15 is 90 into 10 upon 2, we get 900 upon 2, which is equal to 450. Okay, we have the 450 in the options. Okay, it is very simple to solve it like this. Or we can use a lengthy method, rather, that is to use what we call the calculus, that is to use the integrals. So remember, where do we use the integrals? When we have non-linear, both rather one of the non-linear demand or supply function, or both are non-linear. Since our supply function was linear, we were supposed to solve it graphically. If we were told to find out the consumer surplus, we could not have solved it using the graphical method, by obvious reasons, because our demand function is non-linear. Okay, so in that case we would have to use what we call this definite integral method. So if we use the definite integral method, how could we have solved it? So I will not solve it, just to give you an idea. So first, the area of this very triangle, this very region will be equal to, so since so producer surplus, if we use the calculus here, so the area of this whole rectangle will be equal to price, which is price into quantity. So which is equal to price into quantity demand, that is obviously the total revenue, minus then we need to find out the area of this very region. Okay, so it will be simply the definite integral from 0 to 10, so 0 to 10 times rather the definite integral from 0 to 10 of the supply function, that is 15 plus 9x. If we solve it like this, we will get again the same result as 450, but we are not supposed to find out here, because to save the space or time, we can use the graphical method, because our supply function is linear. So why will we make it more difficult? Okay, the question is to find out the equilibrium level of output. If the consumption function is equal to 20 plus 0.8 y subscript d, where y denotes the disposable income, investment is autonomous, which is here 50, government expenditure, which is autonomous, which is 20, and we are being told that we have the tax is equal to 10. We are supposed to find out the equilibrium level of output. Okay, so we know our total income should be equal to the consumption expenditure plus investment expenditure plus government spending. So we also know that consumption function is being given us as 20 plus 0.8. Now what is y subscript d? This is disposable income. Disposable income is simply equal to what we call the total income minus the taxes. Okay, so I guess here the taxes are lump sum. So we have y minus t, plus we have investment, which is 50, plus government spending, which is 20. Solving further, so y will be equal to, so we get 20 plus 0.8 and T is being given us as 10 here, and let's write it here 10. So we will get here 0.8 times y minus 0.8 times 10 is 8, then we have plus 50 plus 20. Transpose this y here, so we get y minus 0.8 y nar lagnu huinen the ms had. So we have 20 plus 20 is 40, so 40 plus 50 is 90. 90 minus 8 is nar lagnu, and 90 minus 8 kodago, that's 82 I guess, sorry, which is 82. Subtract 0.8 y from y, we will get 0.2 y is equal to 82, or 2 upon 10 y is equal to 82, y will be equal to 82. Transpose it here, it gets multiplied but reciprocated, so y will be equal to, so we get 2 1s are 2 5s are 10, 5 2s are 10, 5 8s are 40, which is 410 here. Okay, so the correct option should be 410. Here this shows the tax revenue. We don't have here the marginal tax rate, then we would have the equation like this, y minus a small t times y. Okay, the question is to find out the elasticity of demand. If the demand function is being given us as x is equal to 25 minus 4p plus p square, where x is the quantity demanded, p is the price, then elasticity of demand for price is equal to 5 will be, options are given, we need to find out the correct option. So we have the demand function is x is equal to 25 minus 4p plus p square, and we are being told that price is equal to 5. Okay, we need to find out the elasticity of demand. So first we need to find out the quantity demanded when price is equal to 5. So plug p is equal to 5 here, so we will get x will be equal to 25 minus 4 times 5 plus 25 square, rather 5 square, which is 25, which gives us 25 minus, so we get 50, 25 plus 25 is 50, 4 5s are 20, so we will get 20. Okay, so which is equal to 20. Now we know that elasticity of demand is given by the change in the quantity demanded due to the change in the price into price upon the quantity demanded at that very price. So we need to find out the derivative dx upon dp, that is the change in the quantity demanded due to the change in the price. So taking derivative of this function with respect to p, derivative of a constant is 0, so derivative of p in the second term is 1, so we are left with minus 4, plus derivative of p square is 2p. This is our derivative. Now elasticity of demand will be dx upon dp, which is minus 4 plus 2 times p times p is being given us as 5 upon quantity demanded at that very price is 20. Okay, we also need to plug the value of p here, so e will be equal to, so it is like this, minus 4 plus 2 into p is 20 into 5 upon 20. So we will get here elasticity will come out to be, so we have 20 minus 4. Yes, let me see if I have done it correctly or not. So we get 20, rather p is 5, sorry, p is 5, so we get 2 5s are 10 minus 4, which is 6. It's like this, so we get 2 5s are 10 minus 4 is 6 into 5 divided by 20. Rather it is 30 here. So we have 50 minus 20, which is 30. My mistake. So here we have 30. So we get 30 upon 30, which is equal to 1. So elasticity of demand is 1. That means if price increases by 1%, quantity demanded will decrease by 1%. It is in fact a rectangular hyperbolic demand function. Rectangular hyperbola, that is, we have this kind of demand function where the elasticity of demand is same. The question is to find out the marginal propensity to consume. What is the marginal propensity to consume in the consumption function where C is equal to 40 plus 0.75 Y subscripted? The options are being given. We need to find out the correct option. So C denotes the consumption, which is equal to 40. So 40 is our autonomous consumption when the level of disposable income is equal to 0. Okay, so this denotes the autonomous consumption. Plus 0.75, I will talk about it, times Y. What is Y? Y is our disposable income here. Okay. Now, what is marginal propensity to consume? Marginal propensity to consume is equal to the change in the consumption due to the change in the income. Okay, how much our consumption changes when there is 1 unit or 1% change in our income. That is the derivative of this function with respect to y. Derivative of a constant is 0, derivative of y is 1, so we are left with 0.75. In fact, 0.75 is our marginal propensity to consume. It simply tells us if our income increases by 1 unit or by 1% or 1 unit rather, consumption will increase by 0.75%. Okay. Or let me put it in another way. So the incremental change in consumption due to the change in the income will be 0.75. Every additional dollar or rupee, out of that 75% will be consumed. So the question is to find out the savings function from the consumption function. If consumption is equal to 40 plus 0.75 y, C is the consumption, 0.75 denotes the marginal propensity to consume, 40 is the autonomous consumption when the level of income is 0. Here y is equal to income, rather it is income. We need to find out the savings function here. So we know that our total income is used for consumption and also for the savings purpose. That means y is equal to C plus S. Okay, so we have y will be equal to, consumption is being given the function like this, 40 plus 0.75 y plus we have s here. So solving for s, so s will be equal to, so we have y, then we have minus 0. Or let us write it like this. So s will be equal to, let us transpose this here, it becomes negative 40. Then we have plus y minus 0.75 y. There gives us savings will be equal to minus 40. So subtracting 0.75 y from y, we will get as 0.25 y. That will be the corresponding savings function. The question is, if marginal propensity to import is 0, what happens to the trade multiplier? Options are, it equals the ordinary trade multiplier, it is greater than ordinary multiplier, equal to 0 or less than what we call the ordinary multiplier. So in case of foreign trade multiplier, it is being given by, so let us denote it by M. F, it is equal to 1 divided by the marginal propensity to save plus marginal propensity to import. Now if MPI is equal to 0 in this equation, so our multiplier will be equal to 1 divided by 1, or rather MPS, marginal propensity to save, which is in fact our ordinary multiplier, which we write it in this fashion, that is 1 minus the marginal propensity to consume. Okay, so if MPI is equal to 0, trade multiplier becomes the ordinary multiplier. The question is to find out the Parsh's price index. Suppose the summation of P0 Q1 is equal to 450, summation of P1 Q1 is equal to 519, and summation of P1 Q0 is equal to 415.2. We need to find out the Parsh's price index. Okay, so Parsh's price index, is a consumer price index used to measure the change in the price and quantities of basket of goods and services. It is also called the fixed basket index. It calculates the cost of the specific basket of goods and services in the current period relative to the cost in the base period. That's Parsh's index is being given by, let us denote by P. It is simply equal to the summation of what we call the cost of baskets in the current period, that is P1 Q1, that is price in the current period, quantity in the current period. It is summation, the summation of these baskets, which is P1 Q1 upon relative to the cost in the base period. So base period is P0 Q1, that is P0 Q1. So which will be equal to, so we are being given P1 Q1 is equal to 519 upon P0 Q1, it is 450, which will be equal to, when we solve it will come out to be, so we multiply it by 100. So here we also multiply it by 100, so it will come out to be 1.25 into 100, which comes out to be 125. So this will be the Paaschi's price index. In case of Leontief's price index, that is being given by, that is summation of P1 Q0 upon summation of what we call P0 Q0. Okay, and then we have the Fisher's index. So Fisher's index is simply the geometric mean of L and P. So I will not go into the detail. The question is to find out the correlation coefficient. If covariance of two variables x and y is equal to 10, variance of x is 16, variance of y is 9, find the coefficient of correlation. Options are being given, we need to find out the correct option. So correlation coefficient is being given by, that is equal to the covariance of x and y upon under root of variance of x times variance of y. So covariance is here 10 divided by, we have here variance of x is 16, so let us expand it like this. So here we have 9, so we will get 10 divided by 16 is 4, under root of 16 is 4, and under root of 9 is 3. So we get here 10 upon 4 3s are 12. Solving it further, so we have, this becomes 5 upon 6. So we have 5 here, then we have 6 here. So here we have point, here we have 0. So we get 6 8s are 48 to our left, then we have 0. 6 3s are 18. So we get 0.83. So here we have one option, 0.83. So this should be the correct option. The question is about Hawking-Simon's condition. The correct Hawking-Simon's condition is, options are being given, we need to find out the correct option. Okay, so by Hawking-Simon's condition, it is used in input-output analysis. Okay, so what is I? I is the identity matrix minus A denotes the what we call the technology matrix or input-output matrix. Now the Hawking-Simon condition says the determinant of this, when we subtract the technology matrix from the identity matrix, and when we take the determinant of that very matrix, it should be positive. Okay, so this ensures the viability of the system. Second is, and let me show it with an example here. Let us suppose we have the technology matrix is 0.4, 0.7, 0.1, let us say 0.6. Then we have and I minus A will be equal to then, and let's take the identity matrix as 1 0 0 1. So in this case what happens, we have I minus A. So I minus A will be a matrix that will be 1 0 0 1. From this we subtract this 0.4, 0.7, 0.1, 0.6, this matrix is. So I minus A will be equal to, so 1 minus 0.4 is 0. When we subtract 0.4 from 1, we get 0.6. Here we get 0 minus 0.1 is negative 0.1. then we have 0, here it is minus 0.7, here we get 1 minus 0.6, which is 0.4. okay, this is the matrix here. Now when we take the determinant of this I minus a, it will be equal to, we multiply these two terms first, so we have 6 into 4 is 24, so we get 0.24. then we subtract and multiply these two, so here we get 0.7 into 0.1. what will we get? Okay, so we have 7 upon 10 into 1 upon 10, so we get 7 upon 100, so we get here 0. So what about 0.6? so we have 6 upon 10 into 1 upon 10, so we get 6 upon 100, I guess. Okay, so we have here rather 4. okay, it is perfect. So let us subtract this, so it is 0.07 rather here. So here you can see it is I minus a is positive. okay, it satisfies the viability condition. Second condition is that is the what we call, we should have principal diagonal elements. These are called the principal diagonal elements, and that should be positive. Here we got it positive, it is also positive. So these are the two what we call the conditions. First is that is we should get the positive determinant of this I minus a matrix, and the principal diagonal elements of I minus a should be positive. The question is, what will be the probability of getting more than number 2 by throwing an ordinary die? Options are being given, we need to find out the correct option. So in a die we know there are 6 faces numbered from 1 to 6. okay, so we have 1, 2, 3, 4, 5, 6. The question tells us what is the probability of getting a number more than 2. So this is 1, which is less than 2. More than 2 means we don't need to find out these. So the number of favorable outcomes are 3, 4, 5, 6. So we have 1, 2, 3, 4. So probability of getting a number which is greater than 2 will be equal to the number of favorable events, which are here 1, 2, 3, 4 upon total number of events, possible events, which is here 6, which comes out to be 2 upon 3 in this case. The question is to find out the arithmetic mean. If mode is equal to 27.78, median is equal to 27.73, then arithmetic mean is, options are being given. We need to find out the correct option. So we know the relationship between mean, mode and median is being given by, that is mode. Mode is equal to 3 times median minus 2 times mean. So you just need to plug the value of mean and mode, rather the value of median and mode, to get the value of mean. The question is to find out the output that maximizes the profit of the monopolist. If the demand function of a monopolist is P is equal to 100 minus 2Q, P is the price, Q is the quantity, and cost function is C is equal to 50 plus 20Q, then the quantity of output for the profit maximization will be, options are being given. We need to find out the correct option. So we are here, we have P is equal to 100 minus 2Q. This is the demand function. Cost function is being given as 50 plus 20Q. Profit maximization for monopolist, as we know, we equate the marginal revenue with the marginal cost. Graphically, if I draw the graph, so what we are supposed to do, we have the quantity on the horizontal axis, price on the vertical axis. We have downward sloping demand function. Okay. Then we also, this is our demand function, average revenue function. Then we need to find out the marginal revenue function. Okay, if this is our average revenue function, we are supposed to find out the marginal revenue function for the monopolist. So we need to find out the marginal revenue, and also we need to find out the marginal cost for profit maximization. And let us to find out the marginal revenue, first we need to find out the total revenue, which is equal to price into output. So P is this 100 minus 2Q. To this we multiply by Q, that gives us total revenue as 100Q minus 2Q square. Now marginal revenue will be the derivative of the total revenue function with respect to output, that is the change in the total revenue due to the change in the output. So differentiating this with respect to Q, derivative of Q is 1, we are left with 100 minus derivative of Q square is 2Q, so 2 into 2 is 4Q. This is our marginal revenue. What about marginal cost? Marginal cost is simply the change in the total cost due to the change in the output. That is the derivative of this function with respect to Q. Derivative of a constant, we know it is 0, and derivative of Q in the second term is 1, we are left with 20. Now equating marginal revenue with the marginal cost, we get, which implies 100 minus 4Q will be equal to 20, or 4Q will be equal to 100 minus 20, which is equal to 80, which implies Q will be equal to 80 upon 4, which is equal to 20, I guess. Okay, so if this marginal revenue, so marginal cost is here 20, let us suppose. So this, at this point where quantity demanded is equal to 20, that will maximize the profit of the monopolist. How to find out the maximum profit? The question is, a firm has a production function output which is Q is equal to 12 minus L plus K upon LK, where L and K are the units of labor and capital employed. The prices of labor, capital and output are $1 and $4 respectively, meaning the price of labor and capital are same, which is $1, and price of output is $4. We need to find out the maximum profit. Okay, options are being given, we need to find out the correct option. We know that profit is equal to total revenue minus total cost. Okay, we are being given here that price of labor is equal to $1, price of capital is equal to $4, rather $1 also, and price of output, which is P, is equal to $4. Okay, we know that what will be the cost function of the firm, that will be equal to the price of labor times units of labor employed plus price of capital times units of capital employed. Okay, that will be the cost function. And what about total revenue? We know profit is equal to total revenue minus total cost. So we have profit will be equal to total revenue is price times output. To this we subtract the cost. Here we know the price of labor and capital are same one, so can we write cost will be equal to L. Here we have K, or rather L plus K. Why? Because price of labor is 1, price of capital is 1. So this will be our cost function. From this we subtract the cost function is L plus K. Okay, that implies price is being given as $4, so let's write here 4. Output, that is our production function, is being given as 12 minus L plus K upon LK. Okay, to this we subtract the cost, which is L plus K. So 4 into 12 is 48, minus, then we get 4 times, or let's write it here, 4 into L plus K. Let us write it in this fashion, upon LK. To this we subtract the cost. So we get, when we solve it further, so we get 48 minus 4L plus 4K divided by LK minus L plus K. Solving further, we get 48 minus 4L upon LK, minus into plus is minus 4K upon LK. Then we subtract minus L and minus K. Solving further, so we get 48 minus, here 1L gets cancelled, we are left with 4 upon K, minus here K and K gets cancelled, we are left with 4 upon L, minus L minus K. Okay, let us rewrite it. So we have profit will be equal to 48 minus 4 k raised power minus 1. If I transpose it here, minus 4 l raised power minus 1. If I transpose denominator to numerator, minus l minus k. This is our profit function. Now for maximum profit, what should happen? For maximum profit, marginal profit should be equal to 0. Okay, so for maximum profit, marginal profit should be equal to 0. That is, the change in the profit due to the change in the units of labor employed should be equal to 0. That means we need to find out marginal profit with respect to labor first. So partially differentiating this function with respect to L. Derivative of a constant is 0. Derivative of secondary is also 0. Why? Because we are taking the partial with respect to L. Now derivative of minus 4 L raised power minus 1 will be, minus 1 becomes coefficient, so we get minus 1 times 4, it becomes plus 4. And exponent is subtracted by 1, minus 1 is minus 2. And here the derivative of L is 1, so we are left with 1. And derivative of a constant is 0 because we are taking partial with respect to L. And we set it equal to 0. So can we rewrite it like this? 4 upon L square is equal to 1, or L square is equal to 4, which implies L will be equal to under root 4, or units of labor employed will be equal to 2. Okay. Likewise, we need to find out the marginal profit with respect to capital, and we set it equal to 0. Okay. Now similarly differentiating with respect to capital this time. So derivative of this term, and these terms, rather this term is 0 because we are taking partial with respect to k. Derivative again using power function rule, minus 1 becomes coefficient, so we have minus 1 times minus 4, which becomes plus 4. K raised power exponent is subtracted by 1, we get minus 2, and derivative of k is 1, so we are left with minus 1, and we set it equal to 0, which implies 4 upon k square is equal to 1, or k square is equal to 4, or k is equal to under root 4, or k will be equal to 2. Okay, we are done with this. Now then what will be the, so we need to input, we need to use 2 units of labor and capital to maximize profit. And what is the profit that we are supposed to find out? Having said that, let's find out the corresponding output. So output will be equal to 12 minus L plus K. So L plus K is 2 plus 2 divided by L into K is 2 into 2. So we get output will be equal to 12 minus 4 upon 4. So we get 11 as the 11 units of output should we produce. Okay. Now then total profit will be equal to, so total profit will be equal to, so total revenue price into output minus labor cost, units of labor employed, or we know that price of labor is 1, and we write PL into L, so we have this cost function, and PK into K. So profit will be equal to, so price is being given us as 4, output we found out as 11. From this we separate units of labor and capital that we were supposed to employ is 2 plus 2, so 2 plus 2. So we get here 44 minus 4, which is equal to 40. That means profit will be maximized, that will be the maximum profit. So we don't have 40 in the options, that means we need to add E option, which is 40. Okay. How to find out the extremum of the given function? The question is, find the extremum of u is equal to x square plus y square plus z square subject to x plus y plus z is equal to 1. Okay, we need to find out the optimal values of x, y and z for the given function. Okay, so we will be using the Lagrange's method here. So first thing is what we do to solve this question. So we form the Lagrange's method, Lagrange's function. Okay, so for that what will we do? We take this budget constant first and set it equal to 0. That is, if I set it equal to 0, I will get 1 minus x minus y minus z is equal to 0. then what will I do? We will multiply this both sides by lambda. Okay, then we can form the Lagrange's function, that is L is equal to, so Lagrange's form is equal to the objective function. So this utility function is called the objective function, and to this we add the resulting resulting constraint here. We don't have the budget constraint here, so we have the general constraint. So we have this x square plus y square plus z square. To this we add this constraint that we formed, that is lambda times 1 minus x minus y minus z. This is our Lagrange's function. Okay, since we need to find out the optimum or extreme values, what will we do? We to find out the optimal values of x, y and z, we partially differentiate this Lagrange's function with respect to x, y, z and lambda and set them equal to 0 simultaneously. Okay, so that means, and if I write it here, okay, so to find optimum values, we differentiate this Lagrange's function, we differentiate partially the Lagrange's function with respect to x, y, z and lambda and set them equal to 0. Okay, then we can find out. So let us find out. So L subscript x means the partial derivative of this Lagrange function with respect to x. Derivative of x square will be 2x and derivative of y square is 0, z square is 0 because we are taking the partials. Now in this case derivative of x is minus 1, so we have minus 1 times lambda is minus lambda and we set it equal to 0. Likewise we take L subscript y, that is the partial derivative of this Lagrange's function with respect to y. So we will get 2y minus lambda is equal to 0. Okay, similarly L subscript z means 2z minus lambda is equal to 0, and L subscript lambda means the derivative of this function with respect to lambda. Since no lambda is involved in the first three terms, derivative of lambda is 1, so we are left with 1 minus x minus y minus z is equal to 0. Okay, so can we rewrite these equations here? So can I write 2x is equal to lambda? Okay, and here can I write 2y is equal to lambda, and here 2z is equal to lambda. Let us say this is equation first, equation second, equation third. Okay, so here you can see since RHS of each equation is same, we can equate LHS. This is to say, if we have x is equal to 5, y is equal to 5, z is equal to 5, can we say x is equal to y is equal to z? Yes, we can say. Since we have the same RHS, we can equate the LHS. That implies 2x is equal to 2y is equal to 2z. Okay, so dividing each by 2, so we get x is equal to y is equal to z. Okay, now what will we do? Let us say this is equation 4. So let us put x is equal to y and x is equal to z. Okay, x is equal to y and x is equal to z in this equation. That means 1 minus x, in place of y we write x again, and in place of z we write x again, because x is equal to y is equal to z and which is equal to 0. So put these x's on this side, or let me first write it. So we have minus x minus x minus x, so this is minus 3x is equal to 0, or 3x if I transpose it is equal to 1, or x will be equal to 1 upon 3. So this is the optimal value of x. Now since we know x is equal to y is equal to z, that means y bar will be equal to, or y star, or optimal value of y is 1 upon 3 again, and z is also equal to 1 upon 3. That means x, y, z will be equal to 1 upon 3, 1 upon 3 and 1 upon 3. This is how do we find out the optimal values of a function.